50 million light-years away in the constellation, Coma Berenices lies one of the most peculiar and haunting galaxies ever discovered, the Black Eye Galaxy. In the late 18th century, the night sky was still a mystery, an ocean of faint lights and drifting clouds that astronomers were only beginning to chart. There were no space telescopes, no CCD cameras, no deep sky exposures capturing distant galaxies. All they had were brass telescopes and parchment charts. The discovery of the Black Eye Galaxy. It was during this era, on March 23, 1779, that an English astronomer named Edward Pigott looked through his modest telescope in the constellation Coma Berenices. What he saw that night was a faint, misty patch of light, something that didn't match any of the known stars or clusters. It wasn't sharp, it didn't twinkle. It simply glowed with a soft, ghostly presence. Pigott carefully noted his observation in his journal. A very minute nebula discovered between Beta Comae and another small star, very faint and ill-defined. To the unstrained eye, Coma Berenices was a small, overlooked constellation. But Pigott's curiosity transformed it into a window into the distant universe. He didn't know it then, but he had just become the first human being ever to lay eyes on what we now call the Black Eye Galaxy, catalogued later as Messier 64, or M64 for short. At the time, the word galaxy wasn't even part of astronomy's vocabulary. The Milky Way was thought to be the galaxy, the entire universe. Everything else, these mysterious fuzzy nebulae, were assumed to be gas clouds within our own Milky Way. The true scale of the cosmos had yet to be imagined. But Pigott wasn't alone in his cosmic curiosity. The late 1700s were a golden age of what we now call nebula hunters. Astronomers who combed the night sky for faint, fuzzy objects. Their telescopes were primitive by modern standards, simple refractors with mirrors only a few inches across. But their skill in charting the heavens was remarkable. One of Pigott's contemporaries was Johann Elert Bode, a German astronomer based in Berlin. Bode was known for his passion for cataloguing celestial objects and for promoting what's now known as Bode's law, a rough numerical pattern for the distances of planets from the Sun. But in April 1779, just weeks after Pigott's discovery, Bode independently observed the same faint patch of light. He recorded it as a nebula near the star 35 Coma Berenices, describing it as rather large with a bright center. Neither Pigott nor Bode could have imagined what they were looking at, a massive star-filled spiral galaxy, 50 million light-years away, shining with the combined light of billions of suns. A year later, in March 1780, the famous French astronomer Charles Messier observed the same object. Messier wasn't hunting galaxies, he was searching for comets. His mission was to identify transient moving objects, but again and again he was distracted by these static, hazy patches that cluttered the sky. To avoid confusion, Messier began compiling a list of all the known fixed nebulae, faint cloud-like objects that could be mistaken for comets. His goal was purely practical, to help comet hunters steer clear of false alarms. When Messier pointed his telescope toward Coma Berenices, he found Pigott's faint nebula and added it to his growing catalogue. It became entry number 64, Messier 64, or simply M64. He described it as a nebula without stars, a phrase that perfectly captured what telescopes of his day could reveal. No spiral structure, no detail, just a smudge of light in the void. In Messier's own words, translated from French, nebula discovered in Coma Berenices. It has no star, rather bright at the center, and it becomes imperceptible in a faint glow. Messier could see nothing beyond that pale shimmer, but what he had unknowingly catalogued was a galaxy, one that would later captivate astronomers and astrophotographers for centuries to come. To understand what these astronomers achieved, it's worth remembering just how limited their tools were. Pigott's telescope had a lens no wider than 2 inches. Messier's instruments, though considered cutting edge in the 1780s, had magnifications barely reaching 100x. These were handcrafted instruments, with imperfect optics, no equatorial mounts, and no photography. Observers had to sketch everything they saw by eye under candlelight. And yet, with such humble equipment, they were peering across 50 million light-years of intergalactic space. The light they recorded left the black-eye galaxy when Earth's earliest primates were still evolving. The photons they saw had been traveling across the universe for tens of millions of years before landing in the eyes of an 18th century astronomer in England. What they saw wasn't the galaxy as it was then, but as it had been when dinosaurs still walked the Earth's ancient continents. At the time, the universe was thought to be a single vast Milky Way system. Every star, every nebula, all of it, they believed, existed within the bounds of our galaxy. So to Pigott, Bode, and Messier, M64 was simply another mysterious patch of gas or dust. They had no reason to think it was filled with billions of stars. Even as telescopes improved, the so-called nebulae remained enigmatic. Were they glowing gas clouds within our galaxy, or were they vast star systems beyond it? Astronomers debated fiercely. Some, like William Herschel, believed that nebulae might be made of unresolved stars. Others, including Lord Rosse, suspected something more. In the mid-1800s, telescopes grew in size and sophistication. The most famous of all was the Leviathan of Parsonstown, a giant reflecting telescope built by Irish astronomer William Parsons, the third Earl of Rosse. It was the largest telescope in the world at the time, with a mirror 6 feet across. Lord Rosse turned his Leviathan towards several nebulae and discovered something extraordinary: spiral shapes. The Whirlpool Galaxy, M51, the Andromeda Galaxy, M31, and others revealed swirling structures that looked almost alive. Though the Black-Eye Galaxy wasn't among the first to show clear spirals through Rosse's telescope, it began to be grouped with these new spiral nebulae. Early drawings captured a bright central region surrounded by faint curving arms. But even then, the defining dark band wasn't clearly visible. It wasn't until later, in the late 19th and early 20th centuries, that astrophotography revealed M64's striking appearance. When long-exposure photographs were first taken through larger observatory telescopes, astronomers were stunned. Across its bright oval core was a dark curved lane of dust, as though the galaxy had suffered a cosmic bruise. At the time, no one knew what caused it. Some thought it was a trick of the eye, an imperfection in the telescope mirror. Others suggested it might be a shadow cast by interstellar dust between us and the object. And some wondered if the nebula itself was split, perhaps divided by a band of dark matter or gas. Whatever it was, it looked peculiar, almost bruised. The more observers saw it, the more they commented on its unusual contrast. Most nebulae appeared uniform, softly glowing, but this one had a wound, a black mark across its face. It didn't take long before someone compared it to a black eye, the aftermath of a cosmic blow. The nickname stuck. By the late 1800s, the term Black-Eye Galaxy began to appear in observatory logs and public lectures. The name captured the imagination because it felt so human. Here was a distant galaxy, unknowable, ancient, enormous, and yet its most distinct feature was something we all recognized instantly. A dark bruise, a mark of impact, a scar. Through their telescopes, this galaxy looked like it had taken a punch. But as we now know, what they were really seeing wasn't damage, it was beauty. The dark lane that gives M64 its black eye is made of thick, light-blocking dust, the raw material for new stars. It's not a wound, it's a nursery. A belt of creation wrapped around an ancient spiral. Still, to 19th century eyes, that distinction didn't matter. What they saw was visual drama, a light so bright it was pierced by darkness. It wasn't just another nebula, it looked alive. As the 20th century dawned, a revolution swept through astronomy, the age of astrophotography. For the first time, scientists could capture long exposures, holding the shutter open for hours to let starlight accumulate on glass photographic plates. The result was breathtaking. Details invisible to the human eye leapt into view. One of the first galaxies to truly benefit from this technique was M64. When the earliest photographs of the object were developed in the late 1800s and early 1900s, astronomers were astonished. On the plate, the galaxy was no longer a dim smudge. It was luminous, defined, structured, and across its glowing center ran a stark, inky line. The dark band was far more dramatic on film than it appeared through the eyepiece. What the eye had barely glimpsed, the camera revealed with authority: a crisp, curved shadow cutting across a swirl of light. It was mesmerizing. These images circulated through observatories and astronomy societies, and the name Black Eye Galaxy spread quickly. Journalists loved it. It was simple, striking, and perfectly visual. By the 1920s, it appeared in popular science magazines, often accompanied by grainy black and white photographs showing that eerie contrast between light and dark. The galaxy became famous, not for its size or its shape, but for its face. Even people who knew nothing about astronomy could see why it earned the name. Not everyone agreed that Black Eye was the right name. To some astronomers, it sounded too harsh, too earthly. They saw something more graceful in M64's symmetry, so a gentler nickname emerged: the Sleeping Beauty Galaxy. That name came from its delicate, luminous center, a glowing golden heart surrounded by a smooth disk, half hidden behind a graceful veil of dust. To those observers, M64 didn't look bruised. It looked serene, peaceful, almost resting beneath its dark shroud, like a celestial face in quiet slumber. In other circles, though, especially among amateur astronomers who delighted in the galaxy's eerie appearance through their backyard telescopes, another name surfaced: the Evil Eye Galaxy. Through medium-sized telescopes, the dark lane looked like a narrow slit cutting across a bright pupil, a single watching eye suspended in space. Under certain filters, the contrast deepened, and that resemblance became even stronger. To some, it looked less like a bruise and more like a cosmic stare, something alive, almost supernatural. The Black Eye, the Sleeping Beauty, the Evil Eye. 3 names, 3 moods. Each one reflected how the human mind interprets what it sees, how the same structure could evoke awe, beauty, or fear depending on the imagination behind the telescope. But no matter which name stuck, the feature they described was the same: a perfect collision of darkness and light. When M64 was photographed through large instruments like the Mount Wilson 100-inch telescope, its true nature began to emerge. Astronomers could see spiral arms, bright star-forming regions, and the dark lane in stunning contrast. For the first time, scientists began to suspect that these nebulae were not part of the Milky Way at all, but distant systems of stars, entire galaxies in their own right. This idea, known as the island universe hypothesis, was still controversial. The debate raged for decades until 1923, when Edwin Hubble identified a Cepheid variable star in the Andromeda Nebula. That discovery proved beyond doubt that Andromeda lay far outside our galaxy, and with it, all the other spiral nebulae. From that point onward, M64 was recognized for what it truly is: a galaxy, a vast, independent system of stars orbiting a common center of gravity, billions of stars strong. To understand the significance of the Black Eye Galaxy's discovery, we need to look at the historical context. In 1779, the concept of galaxies did not exist. The term light year hadn't even been coined. Telescopes used no photographic plates. All observations were visual. Astronomers couldn't yet measure distances to stars beyond the solar neighborhood. Astronomy in the 18th century was descriptive, not cosmological. It was about cataloging, not explaining. Messier's list of nebulae was a tool for comet hunters, not an atlas of galaxies. And yet, those faint smudges, Piggot's nebulae, Bode's patches of light, Messier's objects without stars, were silent messengers from other worlds. Without realizing it, these observers had opened humanity's first window into the broader universe. For a long time, Edward Pigot's contribution was overlooked. Charles Messier's name became immortalized through his catalogue, the Messier objects that every amateur astronomer still observes today. But modern historians of astronomy have restored Pigot's rightful place in the story. Pigot was meticulous and methodical, one of the few English astronomers making systematic deep sky observations in that era. His notebooks, preserved today, show an early independent discovery of many objects that later appeared in Messier's list. In recent years, scholars have credited Pigot as the true discoverer of the Black Eye galaxy, predating Bode and Messier's observations. It's easy now, with modern telescopes and dazzling color images from Hubble and the James Webb Space Telescope, to forget just how revolutionary those early discoveries were. Today, when astronomers study the Black Eye galaxy, they see it as a laboratory for understanding galaxy dynamics, dust lanes, and counter-rotating disks. But behind every observation is that lineage: Pigot, Bode, Messier. Observers who didn't know what they had found but knew it was worth noting. Names in astronomy are more than labels. They're emotional shortcuts, ways to connect something distant and complex to something human and familiar. The Black Eye galaxy name worked because it made people feel something before they even knew the science. You don't need a telescope to picture it. The name paints the image for you: light and darkness locked together, beauty with a shadow. It's instantly visual, and for early science communicators, lecturers, writers, teachers, that made M64 irresistible. It was easy to talk about, easy to remember, and visually stunning even in black and white prints. Over time, the nickname shaped how people saw it. When audiences in the 1930s visited planetariums or read illustrated astronomy books, they expected to see a galaxy that looked bruised. They looked for the shadow first, and when they found it, the story became self-reinforcing. The Black Eye became its identity. As technology advanced, astronomers learned that the dark ring wasn't just a random feature. It was a dense lane of dust and gas orbiting the galaxy's core in the opposite direction from its inner stars. This discovery, made through radio and spectral observations in the late 20th century, changed everything. It meant that the Black Eye galaxy had a double structure: two counter-rotating disks, one spinning one way, the other the opposite. The likely cause is a merger billions of years ago, when a smaller galaxy collided with M64 and left behind its gas swirling in reverse. That collision didn't destroy M64. Instead, it scarred it, leaving the very feature that would make it famous. The Black Eye was the visible mark of a cosmic impact. Early misconceptions: the mystery of the nebula without stars. When the Black Eye galaxy was first observed in the late 18th century, astronomers had no idea they were looking at an entire island universe far beyond the Milky Way. To them, it was just another faint misty patch in the sky, a blur among thousands of other nebulae. The instruments of the time were powerful for their era, but compared to modern telescopes, they were little more than magnifying glasses pointed at infinity. The idea that each of these smudges might actually be its own galaxy, containing billions of stars, was unimaginable. Back then, the universe was thought to be small and contained. The Milky Way, as far as scientists could tell, was the universe. Everything visible through telescopes was assumed to be part of it: stars, gas clouds, and glowing patches of light that couldn't be resolved into individual stars. Astronomers like Charles Messier and William Herschel were cataloguing these strange objects not because they understood what they were, but to help other astronomers avoid confusion. The sky was full of comets, and these fuzzy patches could easily be mistaken for one. So Messier's famous list, where M64 would later appear, was meant to prevent mix-ups, not uncover cosmic truths. When Messier observed the Black Eye galaxy in 1781, he recorded it as a nebula without stars, an observation that fit perfectly with what was known at the time. Through his modest telescope, the object appeared faint, diffuse, and lacking any stellar points. there was no hint of the beautiful spiral shape we see today. Messier saw only a cloudy glow, something that seemed to exist between the stars of the Milky Way rather than beyond them. In his notes, there was no mention of motion, structure, or dust lanes, just a soft blur that did not behave like a star or a comet. Even the great William Herschel, who was revolutionizing astronomy by trying to map the Milky Way's shape, had no idea what these nebulous objects truly were. He suspected some might be clusters of distant stars that could, in principle, be resolved with larger telescopes. Others, he thought, might be nebulae proper, vast clouds of glowing gas within our own galaxy. But the idea that these objects might actually be separate galaxies, each one an immense stellar system far away, was still far from anyone's mind. For more than a century, this misunderstanding persisted. Every time astronomers peered at the black-eye galaxy, they interpreted what they saw through the lens of limited technology and limited imagination. Even as telescopes improved through the 19th century, allowing for sharper images and greater magnification, the black-eye galaxy still looked like a patchy cloud of light with a strange dark band cutting across it. That dark feature, the black eye itself, confused astronomers even more. Many believed it to be a shadow, perhaps a dust cloud or absorption feature within the Milky Way, blocking part of a glowing nebula behind it. In other words, they thought the black eye wasn't out there in deep space, but right here, within our own galactic neighborhood. By the mid-1800s, astronomy was undergoing a slow revolution. The first daguerreotype images of the Moon had been taken, and scientists were starting to experiment with capturing light from deep sky objects on photographic plates. But these early techniques were primitive. Long exposures required hours, and the sensitivity of the plates was poor. Still, even the earliest astrophotographers could see that the black-eye galaxy's dark lane was not an illusion. The band of dust was real, thick, opaque, and sharply defined against the brighter background. Yet its true nature remained hidden behind assumptions. At that time, astronomers believed the Milky Way was a flat disk of stars surrounded by clouds of gas and dust. So when they saw a faint, dusty region like the black eye, they naturally thought it was part of that disk, perhaps a cloud of material collapsing to form new stars. It never occurred to them that the entire glowing patch might be another galaxy altogether, spinning far beyond the edge of our own. The confusion wasn't helped by the fact that nebula was a catch-all term. The Orion Nebula, for example, is a massive gas cloud inside the Milky Way, a stellar nursery about 1,300 light-years from Earth. When astronomers compared objects like Orion to the black eye, they seemed similar. Both were luminous, both had irregular shapes, and both could be described as clouds. There was no reason to think one was vastly farther away than the other. Without a clear way to measure distance in space, scientists had no means to prove otherwise. By the late 19th century, larger telescopes were revealing more details, but the central mystery remained. The black-eye galaxy began appearing in more detailed star catalogues, and its strange appearance continued to draw attention. That dark band seemed to defy explanation. Some astronomers suggested that the dark region was the shadow of another nebula in front of a brighter background nebula. Others thought the light itself might be unevenly distributed. Perhaps a region of the cloud had cooled or thickened, absorbing more light than its surroundings. The confusion reached beyond M64. It applied to all spiral-shaped nebulae. In 1845, Lord Rosse used his massive 72-inch telescope in Ireland to observe the Whirlpool galaxy, M51, and discovered its spiral structure. For the first time, astronomers could clearly see that some nebulae had patterns, arms, cores, and symmetry. Yet even then, no one knew what they truly were. Were they parts of our Milky Way? Were they strange stellar systems forming within it? Or were they distant universes, all their own? By the early 20th century, the question had become one of the biggest debates in astronomy. Known as the Great Debate, it culminated in 1920 in a famous public argument between two leading astronomers, Harlow Shapley and Heber Curtis. Shapley believed all nebulae, including the Black Eye, were within the Milky Way. Curtis argued the opposite, that these spiral nebulae were actually island universes far beyond our own. Curtis even cited the Andromeda Nebula, now known as the Andromeda Galaxy, as an example, noting that novae, sudden bright stellar explosions, had been observed there, implying it contained countless stars. But without precise distance measurements, the argument was based on interpretation, not evidence. The Black Eye Galaxy, though discussed less directly, was among the many mysterious objects caught in the middle of this cosmic tug-of-war. The turning point came in the 1920s, when Edwin Hubble used the 100-inch Hooker telescope at Mount Wilson Observatory to observe the Andromeda Nebula. He identified individual Cepheid variable stars, stars whose brightness changes in a predictable pattern that can be used to measure distance. The result was revolutionary. Andromeda wasn't a nearby cloud. It was over 2 million light-years away, far beyond the Milky Way's boundaries. That single discovery shattered centuries of misunderstanding. If Andromeda was an external galaxy, then so were countless other spiral nebulae, including the Black Eye. Overnight, objects like M64 were reclassified. No longer mysterious fogs within our galaxy, but vast systems of billions of stars, each with its own structure, dynamics, and history. For the first time, astronomers could begin to see the Black Eye Galaxy for what it truly was. Its faint light wasn't from gas inside the Milky Way. It was the combined glow of billions of distant suns. The dark band wasn't a shadow across a nearby nebula. It was a dense lane of cosmic dust orbiting another galaxy entirely. The nebula without stars turned out to be filled with more stars than anyone had ever imagined. In retrospect, it's easy to see how early astronomers were misled. They were pioneers operating at the edge of knowledge, limited by their instruments and by the language of their time. The word galaxy itself was still new. It had not yet come to mean what we now take for granted. To them, the universe was smaller, more contained, and more comprehensible. The idea of countless galaxies stretching into infinity was almost inconceivable. But even after Hubble's discovery, the full understanding of M64 took time. It wasn't until much later, with improved spectroscopy and radio observations, that scientists could map the galaxy's structure and motion in detail. Only then did they realize it wasn't just any spiral galaxy. It was a unique one, with a hidden history of collision and counter-rotation. But in those early years, before technology could reveal its secrets, the Black Eye Galaxy remained a symbol of the unknown, a soft, glowing mystery that defied easy explanation. A close look, where it sits in the universe. This galaxy doesn't sit alone in the sky. It occupies a quiet corner of a constellation called Coma Berenices, a faint but historically rich patch of the heavens that has fascinated stargazers for centuries. To the naked eye, Coma Berenices looks like a modest cluster of stars, not nearly as bright or famous as Orion or Ursa Major. But hidden within it is a treasure trove of galaxies, more than 1,000 of them, and the Black Eye Galaxy stands out among them like a jewel surrounded by faint, distant lights. Coma Berenices takes its name from a legend. Ancient astronomers named it after Queen Berenice II of Egypt, who, according to myth, cut off her beautiful hair and placed it in a temple as an offering to the gods. The story says her hair was carried into the sky, where it became the faint cluster of stars we see today. Though that's just mythology, it's fitting that this constellation, named after something as delicate as a strand of hair, would host a galaxy so striking, one with a dark streak running through its bright face. To find M64 in the night sky, astronomers point their telescopes between two neighboring constellations, Canes Venatici, the hunting dogs, and Virgo, the maiden. It's tucked just above Virgo's vast cluster of galaxies, in a quieter region of the sky that's relatively free of bright stars. From our perspective on Earth, the Black Eye Galaxy looks small, only about 1/10 the diameter of the full moon. but that's just because of its distance. In reality, it spans about 51,000 light-years, roughly half the size of the Milky Way. So when you see M64 through a telescope, you're looking across 24 million light-years of space. That means the light entering your eyes or your camera tonight left that galaxy during the late Oligocene epoch on Earth, a time when early apes were just beginning to appear, long before humans evolved. In other words, we are always seeing M64's past. The galaxy itself could look slightly different today than what we see now, but that light has been traveling unbroken for 24 million years to reach us, an ancient message written in photons. Determining that M64 is about 24 million light-years away wasn't easy. For most of history, astronomers had no direct way to measure cosmic distances. It wasn't until the 20th century, when telescopes grew powerful enough to observe certain standard candles, stars whose brightness can be used to measure distance, that scientists could begin to chart the universe in real numbers. For M64, astronomers relied on a type of star called a Cepheid variable. These stars brighten and dim in a predictable rhythm, and by timing their pulsations, astronomers can calculate how far away they are. Using data from the Hubble Space Telescope, scientists refined the black-eye galaxy's distance to around 24 million light-years, with some estimates ranging up to 26 million, depending on the methods used. To give a sense of scale, 1 light-year is about 9.46 trillion kilometers. That means the black-eye galaxy sits roughly 227 trillion kilometers from us. These numbers are so vast that they lose meaning to the human brain. Yet in cosmic terms, M64 is practically our neighbor. It belongs to a region known as the Virgo supercluster, a massive structure of galaxies that also includes our own Milky Way. If the universe were a map, the Virgo supercluster would be our local continent, and the Black-Eye galaxy would be another city on it. Not too close, not too far, but part of the same sprawling cosmic landmass. To truly understand where M64 sits, we have to zoom out, way out, until our entire Milky Way becomes a small dot. When we do that, we start to see the large-scale structure of the universe. Galaxies aren't scattered randomly like grains of sand. They form clusters, filaments, and webs, shaped by gravity over billions of years. The Virgo cluster, which sits at the heart of the Virgo supercluster, is the closest major cluster of galaxies to us, located about 54 million light-years away. It contains thousands of galaxies bound together by gravity. The Black-Eye galaxy, though not a central member of the Virgo cluster, lies on its outskirts, a kind of outer suburb in this galactic metropolis. In astronomical terms, M64 is part of the Virgo supercluster's outer regions, meaning it shares the same general cosmic neighborhood but isn't gravitationally tied to the dense core of the cluster. You could think of it as a town that orbits the edge of a massive city, connected by the same highway of gravity, but living a quieter life away from the bustle. This location gives M64 a certain uniqueness. Being near the edge of the Virgo supercluster means it's less affected by the violent gravitational interactions that occur in denser regions. Galaxies in the cluster's core often collide, merge, or distort each other's shapes due to close encounters. The Black-Eye galaxy, by contrast, exists in a relatively calm pocket of space. Its most recent major collision, the one that gave it its distinctive dark lane and counter-rotating disk, happened about 1 billion years ago, not because of the cluster's influence, but likely due to a smaller satellite galaxy it absorbed long ago. Today, it floats serenely in the cosmic outskirts, shining steadily as one of the most photogenic galaxies accessible to both professional and amateur astronomers. Although M64 appears isolated in telescope images, it's not entirely alone. It's part of a loose collection of galaxies in Coma Berenices, known collectively as the Coma 1 group. This group contains a mixture of spiral and elliptical galaxies, many of which are faint and much smaller than M64. Some of its nearest neighbors include NGC 4414, a grand design spiral galaxy located about 62 million light-years away, and NGC 4559, another spiral with a distorted shape that suggests past interactions. Compared to them, the Black Eye Galaxy stands out for its symmetry and clarity. Its structure appears remarkably well preserved, especially considering that it has experienced a merger in its past. Astronomers suspect that the Coma 1 group itself might be drifting toward the Virgo cluster, slowly falling under its gravitational influence. Over the next few billion years, this region of space could change dramatically, with smaller groups merging into larger clusters, part of the universe's ongoing evolution. From our perspective on Earth, however, all these galaxies appear motionless, frozen in a beautiful still image. In reality, they are all moving at tremendous speeds. M64 itself is receding from us at about 410 kilometers per second, carried along by the expansion of the universe. That might sound fast, but in the context of cosmic motion, it's modest. For comparison, the Andromeda Galaxy, which is much closer to us, is actually moving toward the Milky Way at around 110 kilometers per second. So, while the Black Eye Galaxy is part of our broader cosmic community, it's also slowly drifting farther away, carried by the fabric of space stretching between galaxies. Knowing exactly where M64 sits in the universe isn't just a matter of cosmic geography. It tells astronomers a lot about how it evolved. Being near, but not inside, the Virgo cluster gives it certain environmental advantages. Galaxies that live deep inside massive clusters often suffer from a process known as ram pressure stripping. This happens when a galaxy plows through the hot, thin gas that fills the space between galaxies in a cluster. The pressure of this gas can strip away the galaxy's own gas, quenching its ability to form new stars. Over time, such galaxies fade, turning red and dormant. The Black Eye Galaxy, sitting outside the main body of the Virgo cluster, has avoided that fate. It still contains plenty of gas and dust, allowing it to continue forming stars. This makes it particularly interesting for astronomers studying how environment shapes a galaxy's life cycle. M64 gives scientists a snapshot of what a spiral galaxy can look like when it evolves mostly in peace, undisturbed by the harsher conditions of dense clusters. At the same time, its proximity to other galaxies in Coma Berenices means it hasn't been completely isolated. The collision that produced its counter-rotating gas disks likely came from a small neighboring galaxy that was pulled in by M64's gravity. That event left behind the dark black eye and set off waves of star formation that continue to this day. So, in a sense, M64 occupies a middle ground, not so crowded that it's torn apart by neighbors, but not so lonely that it never interacts. It's a galaxy with just the right amount of cosmic company to stay interesting. For stargazers on Earth, the Black Eye Galaxy apparent brightness or magnitude is around 9.4, which means it's invisible to the naked eye, but well within reach of medium-sized amateur telescopes. From a dark location, away from city lights, you can spot it in late spring when Coma Berenices is high in the night sky. Through a telescope, M64 appears as a small oval glow with a bright core. Under good conditions, a faint shadow, the dark dust lane, can be seen crossing its face, giving it that distinctive black eye look. It's one of the few galaxies where such a dust feature is visible, even in amateur instruments, which is why it's such a popular target among astrophotographers. Modern long-exposure photography reveals its full beauty. When cameras capture hours of light from M64, the spiral structure and the sharp dark lane stand out vividly. The contrast between the bright core and the dark band is what earned it not only the name Black Eye, but also other nicknames like the Evil Eye or the Sleeping Beauty Galaxy. Despite being one of the most photographed galaxies, its distance means we'll never see it change within a human lifetime. Its stars orbit the galactic center over hundreds of millions of years. The spiral arms and dark ring we observe today are nearly the same as they were when our ancestors first looked up centuries ago. From the northern hemisphere, the best time to observe M64 is in late spring, around April and May. That's when Coma Berenices climbs high in the evening sky, away from the glow of the horizon. Around 10 or 11 p.m., the galaxy reaches its highest point, or culmination, making it easiest to observe. Under dark rural skies, with no city lights in sight, it stands out against the black backdrop like a soft smudge of silver smoke. But even in suburban areas with moderate light pollution, dedicated observers can still spot it through small telescopes. One thing that makes the Black Eye Galaxy special is that it's compact and bright for its size. Many galaxies are so spread out that their light is diluted, making them hard to detect visually. M64, however, has a bright central core, which helps it stand out. Its compact brightness also makes it a favorite target for astrophotographers, who love to capture its sharp, dark lane wrapped around the luminous core. The apparent size of the Black Eye Galaxy is about 10 by 5 arc-minutes, roughly a third the size of the full moon as seen from Earth. But remember, that's just how it appears from our distant vantage point. In reality, the galaxy spans around 54,000 light-years across, about half the diameter of the Milky Way. So, when you're looking at that tiny oval through a telescope, you're really seeing the combined light of billions of stars across tens of thousands of light-years, all condensed into a faint smudge. Because of its brightness and distinctive features, the Black Eye Galaxy is often a first target for amateur astronomers transitioning from stargazing to astrophotography. Photographing deep sky objects like this one requires patience, precision, and a good understanding of how to capture faint light over long periods of time. Here's how it's done. Astrophotographers typically use a telescope mounted on a motorized equatorial mount which tracks the rotation of the sky. Because the Earth spins, anything in the night sky moves. So if you just left your camera pointing at the stars, they'd appear as streaks instead of points. The tracking system moves the telescope at exactly the right rate to keep the galaxy in the same position for hours at a time. To capture the Black Eye Galaxy, photographers take long exposure images, often ranging from 3 to 10 minutes each, and then stack dozens, sometimes hundreds, of these exposures together. This process collects more light, revealing the faint details that our eyes can't see in real time. Over time, the faint glow of the spiral arms, the bright bulge at the core, and most importantly, the dark dust lanes start to emerge in the image. That dark band, the black eye, is the result of dense clouds of interstellar dust lying in front of the galaxy's bright nucleus. When light from the stars behind the dust tries to reach us, it gets absorbed and scattered, creating that striking contrast between the bright and dark regions. In long exposure photographs, the effect becomes dramatic. A luminous core slashed by a deep, shadowy curve, like a cosmic bruise frozen in light. Modern astrophotography has pushed this even further. With high-resolution CCD and CMOS sensors, narrowband filters, and advanced image processing software, amateur astronomers can now produce images rivaling those taken by professional observatories a few decades ago. Using filters that isolate specific wavelengths of light, like hydrogen alpha or oxygen 3, photographers can highlight different structures within the galaxy. The dust lanes, the faint halo of stars, even subtle color variations between the older yellowish core and the younger blue star-forming regions in the outer spiral arms, all become visible with enough data and careful editing. In a single frame, with a short exposure, it might just look like a faint blur. But after hours of collecting light, stacking frames, and adjusting contrast, a stunning portrait appears, a luminous eye staring back across millions of light years. It's a reminder that deep sky imaging is not about instant gratification. It's about persistence, collecting photons that have been traveling through space since long before humans even existed. In the best amateur images, the Black Eye Galaxy looks almost three-dimensional, The dark band curls around the bright nucleus like a storm front in space, while the outer arms fade gently into the darkness. The depth and texture in those photos hint at the galaxy's true complexity. That dark dust isn't just blocking light, it's part of a larger story. A ring of gas and dust rotating in the opposite direction of the galaxy's inner stars, evidence of a galactic collision in the distant past. But that's a story for another chapter. Even though astrophotography today feels high-tech, the basic principle behind it hasn't changed since the early pioneers of the field. In the late 19th and early 20th centuries, photographers used glass photographic plates to capture faint light. Exposures could last for hours, often taken in freezing conditions atop mountain observatories. These early images were revolutionary. They revealed structures and details invisible to the human eye. And when the first long-exposure photographs of M64 appeared, that dark lane shocked astronomers all over again. Seeing it so clearly confirmed that it wasn't an illusion or artifact of the eye, but a real physical feature of the galaxy. In those early photographs, the contrast between the bright bulge and the dark lane was so strong that it almost looked unnatural. Astronomers at the time struggled to explain it. Was the dust inside our own galaxy blocking part of M64's light? Or was it dust within M64 itself? As imaging techniques improved, especially with the advent of spectroscopy, it became clear that the dark lane was part of M64, orbiting the galaxy's core, not floating somewhere between us and it. That revelation turned M64 from a curiosity into one of the most studied galaxies in the northern sky. Many amateur astronomers now use GO2 telescopes, which automatically locate celestial objects based on entered coordinates. M64's coordinates, right ascension 12H56, M43S, declination plus 21 degree 41, 00, can be entered into most computerized mounts, instantly pointing the telescope directly at it. Even beginners with small telescopes can capture faint glimpses of the galaxy with the help of digital aids like plate solving, software that aligns the telescope's view with precise star maps. And while nothing beats seeing it with your own eyes, digital imaging has opened a whole new dimension of discovery. Some astrophotographers now create time-lapse composites, showing the galaxy's position in the sky over a full night. Others use color-enhanced imaging to emphasize the chemical makeup of its dust and stars. The core glows a warm yellow-orange, rich in older stars. The dust lane, meanwhile, appears almost black, but sometimes tinged with faint reddish hues, light scattered by microscopic particles of carbon and silicates. One fascinating aspect of imaging M64 is that even modest equipment can produce stunning results. With a telephoto lens and a DSLR camera mounted on a simple star tracker, you can capture not just M64, but also dozens of neighboring galaxies within the same frame. That's because the Coma Virgo region of the sky is one of the richest galaxy fields visible from Earth. Around the Black Eye galaxy, faint smudges of other galaxies, some belonging to the Virgo cluster, fill the background. Each one is a world of its own, and together they form a cosmic landscape that reminds us just how crowded the universe really is. And then there's the satisfaction of knowing that when you capture or observe M64, you're seeing it as it was 24 million years ago. The light entering your telescope left the galaxy back when early mammals were just beginning to spread across Earth, long before humans appeared. Every photon you collect has traveled uninterrupted through space for 24 million years, only to end its journey on your retina or your camera sensor. It's a powerful thought, though simple, factual, and real. For experienced observers using larger telescopes, say 12 inches or more, the view of M64 becomes even more detailed. The galaxy's core shines intensely bright, surrounded by a subtle halo. The dust lane is unmistakable, curving like a crescent over the nucleus. Under excellent seeing conditions, faint hints of the outer spiral arms can even be detected, especially when using averted vision and low magnification. Some observers report seeing the core slightly off-center within the halo, an optical effect caused by the dark band cutting through one side. Because of its brightness and distinctive features, the Black Eye Galaxy is a common sight at star parties, those gatherings where astronomers and hobbyists share telescopes under dark skies. When someone points their scope at M64 and invites others to look, there's usually a moment of silence. It's one of those objects that's hard to describe, but easy to recognize once seen. The black streak across the glowing oval looks almost unreal, like someone smudged ink across a ball of light. Professional observatories, of course, have taken this to another level entirely. Images from the Hubble Space Telescope reveal details no ground-based telescope can match. Fine structures in the dust lane, delicate filaments of gas, and clusters of blue stars embedded along the edges of the spiral arms. These images show that the dark band isn't just a single feature, but a complex system of interwoven dust and gas clouds stretching across thousands of light years. Hubble's sharp vision has even allowed astronomers to map how light from the core is absorbed and re-emitted by the dust, turning a simple visual feature into a powerful diagnostic tool for studying galactic structure. Interestingly, M64's visibility from Earth has made it a calibration target for both professional and amateur astronomers. Because it's relatively bright and has a well-studied structure, researchers often use it to test new imaging techniques or equipment. Radio astronomers, for instance, have used it to measure hydrogen emissions from its spiral arms, while optical astronomers have used its dust lane to study how interstellar material affects the transmission of light at different wavelengths. Even space agencies have made use of it. When NASA's Hubble Heritage Project selected a set of galaxies to showcase the telescope's imaging power, M64 was one of them. The resulting image, released to the public, became one of the most widely circulated galaxy photographs of the early 2000s. A glowing golden eye with a jet-black curve across it, crisp and mesmerizing. That image inspired thousands of amateur astronomers to seek out the galaxy for themselves, sparking a renewed interest in deep sky observation. When we zoom out even farther from the Black Eye Galaxy, we begin to see how it fits into the largest known structure in the universe, the cosmic web. This web is made of countless filaments of galaxies and dark matter, stretching across hundreds of millions of light years. Between these filaments are enormous voids, regions almost completely empty of galaxies. The Virgo supercluster, where M64 resides, is just one node in this cosmic web, and beyond it lies an even larger structure known as Laniakea, a supercluster that includes not just Virgo, but also other major clusters like Fornax and Hydra. In Hawaiian, Laniakea means immense heaven, an appropriate name for a structure that spans over 500 million light-years and contains roughly 100,000 galaxies. Within that grand scale, the Black Eye Galaxy is one of the billions of points of light making up the universe's vast architecture. Its location, though precisely measured in numbers, is best understood in relative terms. It's part of our local cosmic neighborhood, not in the Milky Way's backyard, but close enough that telescopes can study it in remarkable detail. And that detail matters. Because of its distance and orientation, tilted just enough for us to see both its spiral arms and its dust lane, M64 offers astronomers a near-perfect laboratory to study how galaxies evolve after minor mergers. If it were much farther away, that dark band might not be visible at all. If it were much closer, we'd lose the overall view of its spiral structure. In other words, it's positioned just right for us to observe it in full context, both scientifically and visually. In 1990, when the Hubble Space Telescope was launched, M64 was among the galaxies revisited with a new level of clarity. Hubble's sharp vision revealed the complex network of dust lanes winding around the bright nucleus, showing that the dark band was not a single stripe, but a thick, three-dimensional ring of gas and dust orbiting the galaxy's center. Using Hubble data, astronomers also refined the galaxy's distance. Later instruments, like the Spitzer Space Telescope and Galex, added more layers of understanding by observing it in infrared and ultraviolet light. Infrared showed the hidden stars buried behind the dust, while ultraviolet revealed the glowing newborn stars along the ring, a clear sign that M64 is still alive and active. All of this stems from knowing where it sits in space. The exact coordinates, the distance, the orientation, these details form the foundation for every other discovery about the Black Eye Galaxy. Without knowing where it is, we couldn't measure what it's doing, how it's moving, or why it looks the way it does. The Black Eye Galaxy doesn't live in isolation. The neighboring galaxies of M64. The closest notable neighbor to the Black Eye Galaxy is the globular cluster M53, a dense spherical collection of ancient stars that orbits the Milky Way. At first glance, it might sound strange to mention M53. It's not even part of the same galaxy as M64. But on the sky, they appear close together, both lying within the borders of Coma Berenices. When you look through a telescope, you can find M53 only about a degree away from M64, glowing like a tiny concentrated ball of light. It's one of the brightest globular clusters visible from Earth, and though it's actually about 60,000 light-years from us, it gives the illusion of being M64's neighbor. That apparent closeness is what makes this region so striking for observers. You can move your telescope only slightly and jump from one kind of cosmic structure to another, from a tight cluster of ancient stars orbiting our own galaxy to a grand spiral galaxy far beyond. They're unrelated physically, but visually they share the same cosmic neighborhood. It's like looking at two very different worlds through the same window. Moving outward beyond M53, the space around M64 becomes increasingly crowded with other galaxies, each one a member of the Virgo cluster complex. One of the most famous of these is Messier 100, M100, a large and bright grand design spiral galaxy located about 55 million light-years away. M100 lies roughly in the direction of the Virgo cluster's heart and is often considered one of its showpiece members. Through telescopes, it looks like a perfect spiral, symmetric, elegant, with well-defined arms that radiate from a glowing core. Compared to M64, which has a distinctive dark lane and compact form, M100 is broader and more open, with multiple arms filled with young blue stars. It's an active galaxy, rich in star formation, and it has been studied extensively by the Hubble Space Telescope. In fact, Hubble used Cepheid variable stars within M100 to help refine the Hubble constant, the rate at which the universe expands. That makes M100 not just a visual companion in the sky, but a scientific one. Both M64 and M100 have helped humanity measure the scale of the universe. But there's more to their connection than mere coincidence. Though M64 and M100 are separated by tens of millions of light-years, both are influenced by the same gravitational superstructure, the Virgo supercluster. Galaxies in this region don't just sit still, they move, pulled and pushed by the immense gravity of surrounding masses. The Virgo cluster acts as a kind of gravitational anchor, slowly drawing smaller galaxies and groups toward it over cosmic timescales. M64 is on the outskirts of this flow, part of a vast, slow-motion migration that may eventually pull it closer to Virgo's center. Another interesting neighbor is Messier 85, M85, an elliptical galaxy that lies about 60 million light-years away. Unlike M64 or M100, M85 doesn't have spiral arms. Instead, it appears smooth and featureless, a soft oval glow with a bright core. But this calm appearance hides a turbulent past. Astronomers believe M85 formed through the merger of two smaller galaxies, and even now it shows faint ripples in its outer regions, the leftover scars of that collision. This kind of galactic cannibalism is common in clusters, where gravitational interactions are frequent. While M85 is much farther than the Black Eye Galaxy, they both inhabit the same larger environment, an area where galaxies occasionally tug on each other, exchange material, and sometimes collide outright. These interactions, though slow by human standards, are constant on cosmic timescales. and they shape galaxies in dramatic ways. So, has the black-eye galaxy ever interacted with its neighbors? The answer is almost certainly yes, and that's part of what makes M64 so fascinating. When astronomers studied the motion of gas and stars within M64, they discovered something completely unexpected. The inner regions of the galaxy, the bright bulge and the spiral arms near the core, rotate in one direction. But the outer gas disk, stretching tens of thousands of light-years farther out, rotates in the opposite direction. It's one of the most unusual cases of counter-rotation in any nearby galaxy. That kind of motion doesn't just happen on its own. It's the unmistakable sign of a past galactic encounter. The best explanation is that, long ago, M64 merged with a smaller companion galaxy. The smaller galaxy was drawn in by M64's gravity, spiraled inward, and eventually merged with it. But in the process, its gas began rotating in the opposite direction of M64's own. The collision didn't destroy M64, but it left behind this strange dual-motion structure, a galaxy whose heart spins one way while its outskirts spin the other. Over millions of years, the friction between the two regions has caused massive turbulence, compressing gas and triggering waves of new star formation along the interface between them. That's part of what gives M64 its distinctive appearance today. The dark lane and the bright active core are not just visual features, but the aftermath of a cosmic merger. What's intriguing is that this collision likely happened with a galaxy that once shared the same neighborhood, perhaps one of the many smaller galaxies that still populate the Virgo supercluster's outskirts. In deep images, faint streams of stars, called tidal tails, have been detected around M64. These are the shredded remnants of the smaller galaxy it devoured. Over time, the stars from that galaxy have mixed into M64's halo, while its gas settled into the counter-rotating disk we observe today. If we think of the black-eye galaxy's surroundings as a busy cosmic highway, then M64 is like a driver that once collided with another car, but kept moving, carrying part of the wreckage along. The scars are still visible, written in the motion of its gas and dust. And somewhere in the vastness of Coma Berenices, there may still be other survivors of that ancient event, smaller galaxies that felt the gravitational tremor but escaped complete destruction. Astronomers have found hints of smaller satellite galaxies and faint companions near M64, though none are major enough to rival it in brightness. These dwarf galaxies are difficult to detect, often appearing as faint smudges even in deep exposures. But their existence is important because such small companions can still interact gravitationally with M64, stirring its outer halo and subtly altering its shape over time. Some simulations suggest that galaxies like M64, located near the outskirts of massive clusters, are constantly influenced by the gravitational tides of their environment. These tidal forces can stretch and warp the outer parts of galaxies, pulling faint streams of stars into intergalactic space. Observations of M64's surroundings have revealed traces of such faint extensions, ghostly arcs of starlight that may represent material being slowly stripped away by the larger Virgo cluster's gravity. To understand just how complex this region is, consider that within a patch of sky only a few degrees wide, the area covered by the constellations Coma Berenices and Virgo, there are thousands of galaxies. Many of these belong to small groups orbiting larger systems. Others are independent, drifting alone through space. The black-eye galaxy happens to lie right where these different gravitational territories overlap, on the edge of a supercluster, but not bound tightly enough to be pulled into its core. It's in a kind of cosmic borderland. This location makes M64 scientifically valuable. Because it's not buried inside the dense heart of the Virgo cluster, where galaxies are often stripped of their gas and distorted by collisions, it has retained its spiral shape and much of its original structure, but at the same time, its environment is active enough that past interactions, like the one that caused its counter-rotation, are still likely. That balance, isolation mixed with interaction, makes the black-eye galaxy a kind of transitional object, a glimpse of how environment shapes galactic evolution. To visualize it better, imagine standing on an imaginary point above the Virgo supercluster and looking down. At the center, you'd see the bright, crowded Virgo cluster itself, a swarm of galaxies clustered tightly together, dominated by giants like M87, a massive elliptical galaxy with a supermassive black hole at its core. Around this dense hub, the number of galaxies begins to thin out. Moving outward, you'd pass through smaller groups, each connected by tenuous bridges of dark matter. Then, far from the center, you'd reach galaxies like M64, orbiting at the edges, drifting in quieter space, influenced but not consumed by the gravity of the cluster. In deep surveys, like those conducted with the Sloan Digital Sky Survey and Pan-STARRS, the region around M64 shows faint structures linking it to these larger cosmic filaments. These are not visible through backyard telescopes, but sensitive instruments can trace the distribution of faint galaxies and dark matter around it, showing that M64 is part of a web, one thread in a network that connects countless galaxies across tens of millions of light-years. What's especially fascinating is how different galaxies within this same region can look. M53, as mentioned earlier, is a globular cluster, compact, old, and orbiting within our Milky Way. M100, by contrast, is a bright, vigorous spiral with active star-forming regions. M85 is an old elliptical, smoothed out by mergers. And then there's M64, smaller than M100, but with a more complex internal structure, a product of collision and adaptation. Together, they show the full spectrum of galactic diversity in one patch of sky. This diversity isn't random. It reflects the environments each galaxy inhabits. In dense regions like the Virgo cluster's core, galaxies are constantly colliding, merging, or losing gas through tidal stripping and interactions with the hot intracluster medium. The result? Smooth, gas-poor ellipticals like M85. Farther out, where collisions are less frequent but still possible, spirals like M64 can survive while still showing signs of past encounters. And in isolated areas even farther from the cluster, pristine spirals like M100 continue to thrive, forming new stars freely. What makes the black-eye galaxy particularly captivating is that it stands at that crossroads, not untouched by its environment, but not destroyed by it either. It has endured interaction and come out looking both beautiful and scarred. Its location near these other galaxies gives astronomers a chance to study how galactic ecosystems evolve, how gravity shapes not just individual galaxies, but entire cosmic regions. And while we often talk about galaxies in terms of light years and distances, there's something remarkable about realizing how they influence one another even across those vast separations. The gravitational pull of M85, or the Virgo cluster's central mass, may be weak compared to M64's internal gravity, but over billions of years, even small tugs add up. The orbits of stars in the outer halo, the motion of gas, and even the direction of rotation can all carry signatures of these slow, distant interactions. Some astronomers have proposed that M64 might once have been part of a small group that was gradually disrupted by the Virgo cluster's pull. In this scenario, the smaller galaxy it absorbed could have been a former companion drawn in as the group fell apart. If that's true, the faint streams around M64 are not just remnants of one merger, but the leftovers of an entire system being dissolved into the larger supercluster. In cosmic terms, it's a story of migration. Galaxies drifting toward denser regions, colliding, and reshaping each other in the process. Even now, M64's motion through space tells part of that story. It's moving relative to us at a velocity of about 410 kilometers per second, based on the redshift of its light. That's roughly 1.5 million kilometers per hour. Though that speed seems staggering, in cosmic terms it's moderate, part of the general flow of galaxies being drawn toward the Virgo cluster's center. It's not heading directly at us or away from us, but sideways, in a kind of orbital drift that keeps it within the gravitational influence of the supercluster. The structure of the Black Eye Galaxy. At first glance, M64 looks like a perfect spiral galaxy, but astronomers classify it more precisely as SAR's AB, a code that reveals a lot about its internal design. Let's break that down. The S tells us it's a spiral galaxy, one of the most common galaxy types in the universe. Spirals are like giant rotating disks of stars, gas and dust, with arms that wind outward from a central bulge. They are the galaxies most of us think of when we imagine the night sky's distant islands of light, graceful, organized, and full of life. The next letter, A, tells us that this spiral has no large central bar of stars cutting through its center. Barred spirals, like our Milky Way, have a bright bar-shaped core from which the arms extend. But M64 doesn't have that strong bar. Instead, it has a softer, rounder nucleus. Still, there's a hint of structure there, something almost bar-like, hence the small addition in parentheses. That's where the RS comes in. It means M64 has a ring-like structure, that's the R, blended with a spiral pattern, that's the S. You can think of it as a hybrid, spiral arms that don't simply radiate out, but form a faint circular ring around the central bulge. The result is a galaxy that seems both organized and a little hazy at the same time. It spirals tight, but not overly rigid. Finally, the AB indicates that the spiral arms are tightly wound, but not so tight that they completely wrap around the core. On the spiral scale, A galaxies are very tightly coiled, while C galaxies are open and loose. AB is somewhere in between, still snug, but starting to loosen just a bit. M64's arms circle gracefully, like the curves of smoke rising in slow motion before trailing off into faint, misty outer regions. Put it all together, and that single code, SAR's AB, tells us that the Black Eye Galaxy is a tightly wound spiral galaxy with a faint ring structure and a mostly unbarred core. It's ordered, elegant, and just a touch unusual. Now, as for its size, M64 has a diameter of about 51,000 light-years. That's a huge distance, but compared to the Milky Way, it's only about half as wide. If you could place M64 next to our own galaxy, the Milky Way would stretch twice as far across space. But don't let that fool you. M64 still contains hundreds of billions of stars and enough mass to bend light and pull smaller galaxies into its orbit. It's smaller, yes, but still immense beyond imagination. To put that into perspective, light, moving at the fastest speed possible, takes 51,000 years just to travel from one side of M64 to the other. If you sent a beam of light from one edge to the other when early humans were painting caves in France, it still wouldn't have reached the far side by now. That's how vast this single galaxy is. In terms of mass, astronomers estimate that M64 contains around 100 billion solar masses. That's 100 billion times the mass of our Sun. Most of that mass is in the form of stars, but some of it is gas, dust, and an invisible halo of dark matter that surrounds the galaxy like a ghostly bubble. This dark matter doesn't emit light, but its gravity helps hold the galaxy together, keeping its stars moving in their graceful orbits rather than flying off into space. When scientists measure the rotation of M64, they find that the galaxy spins in an orderly fashion, like a cosmic pinwheel. But there's a twist, literally. The gas in the outer regions rotates opposite to the direction of the inner stars and gas. It's as if the galaxy's outer layer is going one way, while the core spins the other. That strange counter-rotation tells astronomers that M64 didn't always look the way it does now. It probably merged with another galaxy long ago, swallowing its smaller neighbor and absorbing its gas, which settled into an opposite spin. The visible structure we see today, the graceful spiral arms and that dark streak across the center, are the result of that ancient cosmic collision. From afar, though, you wouldn't immediately guess all this. Through a telescope, M64 looks like a smooth, luminous disk, glowing softly in shades of white and yellow at the center, fading to pale blue and gray near the edges. The dark eye across its heart is the feature that catches your attention first, a thick band of cold dust that blocks the light from the stars behind it. This dust isn't empty, it's made of carbon, silicate grains and gas, the raw materials for forming new stars. It's both a shadow and a birthplace. If you zoom in toward the very center of M64, past the spiral arms and through the dark dust lane, you arrive at its central bulge, the heart of the galaxy. The bulge is a dense, rounded region made mostly of old stars. These stars have been shining for billions of years, long before the Sun, before Earth, before our solar system even existed. Their light has a warm golden yellow tone, a sign of their age. They are cooler, older stars, red giants and yellow main sequence stars, rather than the hot blue stars found in the spiral arms. The color difference is like comparing the steady glow of embers to the flicker of fresh flames. Astronomers estimate that the stars in M64's bulge are about 9 to 12 billion years old. That means many of them formed when the universe itself was still young, only a few billion years after the Big Bang. These ancient stars give the bulge its mellow glow, like the golden haze of an old photograph. The light we see from them today left the galaxy 24 million years ago, but the stars themselves had already lived through countless cosmic events by then. The bulge of M64 isn't just a random clump of stars. It's a dynamically hot system. That means the stars move in all directions, not in the flat, ordered paths of the disk. If the spiral arms are like cars moving smoothly around a circular track, the bulge is more like a busy city intersection, with stars moving in every direction, bound together by gravity but following complex orbits. The result is a rounded, three-dimensional shape that gives the galaxy its bright, solid center. Deep within this bulge, at its absolute core, astronomers believe there lies a supermassive black hole, the hidden engine that anchors the entire galaxy. It's not visible directly, but its presence is inferred from the motion of stars near the center. The stars whip around the core at incredible speeds, faster than can be explained by visible mass alone. Something massive and compact must be there, a black hole millions of times the mass of the Sun. The black hole's gravitational influence doesn't just pull stars inward, it helps shape the structure of the inner galaxy. It can trigger star formation, regulate gas flow, and even create jets of high-energy particles when matter falls toward it. In M64, there's no large jet or outflow visible, suggesting the black hole is relatively quiet right now, resting, so to speak. But it likely played a more active role in the past, especially during the galaxy's formation and its merger events. Around the bulge, the inner disk of M64 begins to take form. This region marks the transition from the dense old stars of the core to the younger, bluer stars of the spiral arms. It's also where the rotation pattern becomes clear. The stars and gas here orbit in one direction, forming a smooth, tightly wound spiral pattern that gives M64 its classification as AB. This inner disk glows with a subtle gradient of light, bright at the center, fading outward. The light profile follows an exponential curve, meaning the brightness drops rapidly with distance from the core, but never truly ends. Even at the faintest edges of the visible disk, scattered stars continue to orbit, thinning into the halo. The bulge itself is surprisingly compact compared to the galaxy's overall size. If M64's full diameter is 51,000 light-years, the bulge might extend only a few thousand light-years across, like the glowing nucleus at the center of a spinning record. But in terms of mass, it's one of the heaviest parts of the galaxy. Billions of stars are crammed into that small region, packed so tightly that their collective gravity dominates the galaxy's heart. Because of its high density, the bulge also acts like a stabilizer, keeping the inner spiral arms anchored and maintaining the galaxy's balance. Without that mass in the center, the spiral pattern might not hold its shape over billions of years. The bulge's gravity ensures the whole system moves together, like a dancer keeping her balance around her center of gravity. What makes M64's bulge visually distinctive is how sharply it contrasts with the dark dust lane that crosses it. That dust lane, the galaxy's namesake black eye, cuts across one side of the bulge like a bruise or a shadowed eyelid. It's made of dense molecular clouds, cold opaque material that absorbs starlight. The effect is so striking that even small telescopes on Earth can detect it clearly. The bright golden light of the bulge is sliced by a band of darkness, giving M64 its eerie, mesmerizing look. But that dark band isn't just a random cloud drifting by. It's part of the galaxy's inner ring, a structure formed where gas from the counter-rotating outer disk meets the inner region. Where the two layers of gas collide, they compress, creating dense molecular clouds that can eventually form new stars. In other words, that dark lane might also be a cradle for future light. So, even though the bulge is dominated by old stars, it's surrounded by a dynamic zone where new stars are being born, where the galaxy's past and future meet. Astronomers studying M64 in infrared and radio wavelengths can see through that dust and map the gas hidden inside. They find complex patterns of motion, turbulence, and shock waves, evidence of the ongoing friction between the inner and outer disks. The bulge may look peaceful in visible light, but underneath it's a region of constant activity, with gas clouds colliding and stars forming in bursts along the dust lanes. The bulge's color also tells a story about its chemical makeup. Older stars tend to have lower metallicity. That means they contain fewer elements heavier than hydrogen and helium. These metals are forged in stars over time and scattered into space through supernova explosions. So a low metal bulge means that its stars formed early, before many generations of stars had enriched the galaxy's gas. In M64, the bulge's yellow tone and spectral signatures confirm that it's ancient and relatively metal-poor compared to the younger spiral arms. It's like an archaeological layer at the bottom of a cosmic timeline. The smoothness of the bulge contrasts beautifully with the texture of the surrounding dust. The inner light appears almost creamy, uninterrupted, while the dark band that crosses it has visible structure, filaments, wisps, and knots. High-resolution Hubble images show these details clearly, revealing that the eye is made of multiple overlapping clouds rather than one continuous sheet. Each cloud spans several light years, containing enough gas and dust to form thousands of stars. Seen together, they create the illusion of a single, heavy shadow. Because the dust absorbs visible light, astronomers use other wavelengths, like infrared, to peer through it. When they do, the structure beneath becomes clear. The bulge continues smoothly behind the dust, undisturbed, its stars shining faintly through the haze. That means the dark lane doesn't cut into the bulge physically. It only blocks our line of sight. From another angle, M64 might look completely different. Its eye invisible, its face unscarred. In fact, that's an interesting thought. If intelligent beings in another galaxy were looking at M64 from a different direction, they might never notice its famous black streak. To them, it might look like a normal spiral galaxy, symmetrical and clean. The eye exists because of perspective, because we happen to view it edge-on enough to see that dense lane of dust across the bright core. In that sense, the galaxy's most recognizable feature is also partly an illusion, shaped by our viewpoint. Still, even illusions can reveal truth. The dark lane shows us where the gas is, where star formation happens, and where the galaxy's structure changes from old to new. It's a reminder that the Black Eye galaxy is layered, not just in age, but in motion and composition. The central bulge remains the most stable part of that system. While the outer regions twist and collide, the bulge endures, glowing steadily. It's the memory of what the galaxy used to be, a fossilized remnant from its early days, surrounded by younger, livelier arms. Within that dense heart, stars move in every direction, their paths crossing in a complex gravitational dance, all centered around the quiet, invisible pull of a black hole that keeps everything bound. If we could hover near the bulge, somehow surviving the radiation and crushing gravity, we'd see a sky unlike anything around Earth. The stars would be thousands of times closer together. The night would never be dark. Everywhere you looked, there'd be light, yellow suns crowding the sky, blending into one another until the horizon glowed continuously. Shadows would vanish. Day and night would blur. The airless void would shimmer with the collective light of billions of ancient stars, all orbiting in slow, stately paths. And at the very center, where the light grows faint and red, there would be the domain of the black hole, invisible but powerful, shaping everything around it. The spiral arms of the Black Eye Galaxy. At the core of Black Eye Galaxy lies its spiral arms, two grand sweeping structures filled with life, color, and cosmic activity. They are the highways of starbirth, the rivers of gas and dust that fuel creation, and the very reason this galaxy gleams so vividly in telescope images. The Black Eye Galaxy's arms are tightly wound, a trait common in early-type spiral galaxies. Unlike galaxies with loose, sprawling spirals, M64's structure looks more compact. Its arms wrap closely around the glowing nucleus, giving it that graceful, tightly coiled appearance. When astronomers classify it as type SAR-IRS AB, that AB indicates its intermediate tightness. To our eyes, this means its spiral arms are neither open and loosely scattered, nor hidden in a featureless disk. They are well-defined, elegant, and visually striking. When we talk about spiral arms, we're not describing something solid or permanent like roads. Instead, these arms are density waves, areas where matter becomes temporarily compressed as it orbits the galaxy's center. Imagine cars on a highway moving at different speeds. Where traffic slows, cars bunch up, creating a denser region. Spiral arms work in a similar way. Gas, dust, and stars flow through them, getting squeezed by gravity, and that compression ignites star formation. The result? Long curved regions glowing with clusters of young, hot blue stars, the very signatures that make M64 shimmer with life. What's fascinating about M64's spiral arms is how clearly they reveal two stages of stellar life. If you could zoom in, you'd notice bright blue clusters. These are the youngest stars, burning fiercely but briefly. Alongside them are pinkish patches, glowing clouds of ionized hydrogen gas known as H2 regions. These are nebulae where new stars are forming right now. Ultraviolet radiation from newborn stars excites the surrounding hydrogen, making it glow with that soft pinkish hue that astrophotographers love to capture. It's a universal sign of creation, light born out of dust and gas. Every H2 region in the Black Eye Galaxy tells the same story. A cloud of hydrogen collapses under its own gravity until the core becomes dense and hot enough for nuclear fusion to begin. The gas around it begins to glow, tracing the edges of the galaxy's spiral arms like neon lights marking the curve of a highway. These regions can span hundreds of light years and may contain thousands of stars in various stages of formation. In M64, these bright patches are concentrated along the inner spiral arms, especially near the dark ring of dust that gives the galaxy its famous black eye. That dark ring isn't just decoration, it's the fuel line for the arms. Inside that dust lies cold molecular hydrogen, the raw material for new stars. As the spiral arms sweep through this dusty region, they compress the gas, triggering bursts of star formation. The result is a cycle of creation that continues endlessly. Older stars drift out of the dense regions into the galaxy's disk, while new generations ignite behind them. Over millions of years, this process gives the spiral arms a kind of rolling, wave-like motion, always changing, always producing light. Observations from telescopes such as Hubble have given astronomers a front-row view of this process. Images show the inner spiral arms glowing in soft blue and white, dotted with pink nebulae, while the dark ring creates sharp contrast. You can see how the arms seem to emerge from beneath the shadowed dust lane, winding outward before fading into the galaxy's faint outer halo. It's this mixture of darkness and brilliance that gives M64 its haunting beauty, a galaxy both calm and turbulent at once. Another remarkable aspect of M64's spiral structure is how it connects to the galaxy's internal rotation. For most galaxies, gas, dust, and stars all move in the same general direction, but in M64, astronomers discovered something unusual. The gas in the outer regions rotates in the opposite direction of the gas and stars in the inner disk. This counter-rotation creates immense shear forces at the boundary, stirring up turbulence and compressing gas, again feeding into star formation along the spiral arms. It's almost as if the galaxy's two halves are moving against each other, creating friction that sparks new light. This counter-rotation likely has a dramatic origin. Scientists believe that M64 merged with a smaller galaxy sometime in its past, perhaps a few billion years ago. The smaller system's gas was absorbed, but it retained its original spin, opposite to that of M64's disk. Over time, the two motions began to mix, creating the chaotic interface we now see. That collision may have been the event that intensified the galaxy's star formation, giving rise to the striking spiral arms and the dark swirling dust ring that defines its face today. The evidence for this ancient encounter can be seen in the way the spiral arms behave. Near the center, they appear smooth and tightly wound, filled with older stars and steady star-forming regions. But further out, the structure becomes more disturbed, as though the outer arms are twisted or uneven. Radio observations of hydrogen gas reveal streams and filaments that don't align perfectly with the inner disk, hinting at leftover material from that long-ago merger. Despite that violent past, the Black Eye galaxy has achieved a kind of balance. The spiral arms remain active but stable, and the star formation rate, though vigorous, is not chaotic. In fact, M64 produces new stars at a rate of about 1 solar mass per year, similar to the Milky Way's pace. That may not sound like much, but across the vast expanse of the galaxy, it's enough to keep the spiral arms glowing steadily. Within those arms, stellar nurseries burst to life in clusters. Some form open star clusters, loose gatherings of a few hundred young stars. Others produce massive stars that live fast and die spectacularly as supernovae, enriching the surrounding gas with heavy elements. These explosions inject energy back into the spiral arms, pushing gas outward, shaping the next generation of star formation. It's a feedback loop that sustains the galaxy's evolution. If you could fly through one of M64's spiral arms, the view would be breathtaking. You'd pass through fields of brilliant blue stars, each shining tens of thousands of times brighter than the sun. Between them, you'd see dense clouds of gas glowing in red and pink, where new stars are forming behind curtains of dust. Every direction would reveal evidence of movement, rotation, turbulence, and light flickering through filaments of interstellar matter. And above it all, that dark dust ring would hang like a shadowed veil, hinting at the powerful processes underneath. The structure of these arms also affects how light escapes the galaxy. Dust within the arms absorbs and scatters visible light, but infrared observations can pierce through, revealing stars hidden from optical telescopes. When astronomers use instruments like the Spitzer Space Telescope to study M64 in infrared wavelengths, they uncover a more complete picture, one where the spiral pattern extends further out than it appears in visible light. It's like switching from a flashlight to night vision. Suddenly, the hidden framework of the galaxy comes into view. Interestingly, even though M64's spiral arms are rich in gas and dust, they don't extend endlessly outward. Beyond the visible arms lies a faint halo, a region where stars are sparse and the density of gas drops sharply. That outer zone marks the edge of the galaxy's active disk. Beyond it, gravity still binds faint stars and dark matter, but the creative energy of the spiral arms fades away. Yet even here, astronomers detect traces of hydrogen, suggesting the remnants of the smaller galaxy that once collided with M64 still linger in orbit. One of the most captivating details about the Black Eye galaxy's spiral structure is how it interacts with its central dust ring. In many spiral galaxies, dust lanes trace along the inner edges of arms, outlining the curves. But in M64, the dust collects in a thick, nearly complete ring that partially obscures the inner arms. The effect is dramatic. The galaxy appears to have a shadowed core surrounded by a bright halo of starlight. When viewed through telescopes, the dark lane cuts across the galaxy's bright center like a bruise or smoky band, the very feature that inspired its name. That ring, dense with molecular gas, is the cradle of the galaxy's most active star formation. It acts like a dividing line between the inner and outer spiral arms, where turbulence and rotation differences collide. In some regions, the gas clouds are so dense that starlight barely escapes, while in others, supernova blasts have cleared small windows through the dust, allowing the bright blue light of newborn clusters to shine through. Every image of M64 captures that tension between light and shadow, birth and obscurity. Even today, astronomers continue to refine our understanding of these arms using high-resolution imaging. Instruments on the Hubble Space Telescope, the Atacama Large Millimeter Submillimeter Array, ALMA, and even large amateur observatories on Earth keep revealing new details. Some of these studies show evidence of star-forming knots, small, localized bursts where the gas density spikes. Others map the distribution of carbon monoxide and hydrogen molecules, tracing where the next stars are likely to appear. It's also through the spiral arms that M64's rotation can be measured. By studying the Doppler shift of light from gas clouds, astronomers can see one side of the galaxy moving towards us and the other moving away. This rotation curve reveals that the inner disk rotates at speeds of around 200 kilometers per second. Further out, in the counter-rotating region, the speed drops and reverses direction. That observation helped confirm the galaxy's unusual dynamics and offered clues to its merger history. Each turn of those arms represents millions of years of cosmic motion. Stars born in the inner regions will drift outward as the arms rotate, slowly aging as they move. After billions of years, they'll leave behind traces of heavier elements, oxygen, carbon, and iron, enriching the galaxy's chemical composition. The dark ring, the signature shadow of the Black Eye galaxy. When people first see an image of the Black Eye galaxy, the feature that immediately draws attention isn't its spiral arms or golden core, it's that unmistakable dark ring slicing across the center. Like a cosmic bruise or shadowed scar, this ring defines M64's identity. It is what makes it stand apart from countless other spiral galaxies that populate the night sky. To astronomers, this ring isn't just an odd visual detail. It's a dynamic, living structure made of gas, dust, and energy, the very material from which stars are born. The Black Eye galaxy's dark ring is almost perfectly circular, wrapping around the bright, glowing central bulge like a band of shadow. In visible light, it appears nearly black, an opaque belt that hides the starlight behind it. But what looks like darkness is actually something far more complex. That ring is filled with molecular hydrogen, cold interstellar gas, and countless microscopic grains of dust, the same building blocks that form new suns and planetary systems. To the naked eye, or even small telescopes, the contrast is so sharp that it seems as if someone painted a dark stroke across the galaxy's bright face. In the 19th century, when astronomers first noticed this feature, it created confusion. Early observers using ground-based telescopes could see the bright nucleus and faint spiral structure, but the dark lane puzzled them. Some speculated that it was a shadow or perhaps a void, a region where no stars existed. Others thought it might be a foreground cloud within our own Milky Way, blocking the light of a distant nebula behind it. Without the benefit of spectroscopy or space-based imaging, there was no way to tell. It wasn't until the mid-20th century, when photographic plates became more sensitive and radio astronomy began to develop, that the true nature of the dark ring started to reveal itself. Astronomers realized it wasn't a gap in the galaxy, but rather a dense region of interstellar matter, a ring of cold molecular gas and dust orbiting the galaxy's center. In other words, it was part of M64 itself. The Black Eye Galaxy wasn't missing light. It was hiding it behind layers of cosmic debris. Modern observations show that this dust lane is made up of extremely fine particles, mostly silicates and carbon compounds, mixed with cold hydrogen gas. These particles are only a fraction of a micron in size, but together they're thick enough to absorb visible light from the stars behind them. The result is the dark band we see from Earth. Infrared and radio telescopes, however, can peer through that dust. In those wavelengths, the ring glows faintly, revealing that it's far from empty. It's actually one of the most active regions of the entire galaxy. Within that dark ring lies a massive reservoir of molecular hydrogen, the raw material for star formation. The gas is cold, typically only a few tens of degrees above absolute zero, and in such an environment, gravity can easily cause clumps to collapse into new stars. The dark ring, therefore, functions as a giant stellar nursery, a place where thousands of young stars are being born every few million years. When viewed in high-resolution imagery from the Hubble Space Telescope, the structure of the ring is astonishingly detailed. It isn't smooth or uniform. Instead, it's laced with filaments, knots, and arcs, evidence of turbulence and shock fronts. These shock fronts form where gas clouds collide or where supernova explosions from older stars send waves of energy rippling through the interstellar medium. Each ripple compresses gas, setting off another wave of star formation. The result is a dynamic, ever-changing region that constantly recycles itself. In these Hubble images, astronomers can also trace faint streaks of pink and red embedded in the dark dust. These are the telltale signs of H2 regions, clouds of ionized hydrogen, where young, massive stars are already shining. Their radiation carves out small cavities in the dust, illuminating their surroundings. It's an incredible contrast. Bright, hot light trapped within deep, cold darkness. Every glowing patch marks the birth of a new cluster of stars, some of which will eventually drift outward to join the spiral arms. The ring also plays a critical role in shaping how the galaxy evolves. Because it contains so much mass, its gravity influences the motion of nearby gas and stars. Studies show that gas in the inner disk of M64 rotates in one direction, while gas in the outer disk, beyond the dark ring, rotates the opposite way. The boundary between these two layers, right where the dark ring lies, is a zone of intense turbulence. The opposing motions create shear forces that churn the gas and dust like two ocean currents colliding. This turbulence is one of the reasons the ring is such an active star-forming region. It's rare to see such strong counter-rotation in a spiral galaxy. Most likely, it's a result of a galactic merger that happened a few billion years ago. The Black Eye Galaxy may have absorbed a smaller companion galaxy whose gas was rotating in the opposite direction. The collision mixed the two systems, but their gases kept their original spin. Over time, the interaction created the dark ring as the boundary zone where the two flows meet. This ancient collision not only gave M64 its distinctive black eye, but also jump-started a long period of star formation that continues today. Radio telescopes studying carbon monoxide emissions, one of the best tracers of molecular gas, have mapped the structure of the dark ring in exquisite detail. These maps show that the ring contains several 100 million solar masses worth of gas, distributed unevenly across its circumference. Some parts are denser and more active, hosting dozens of compact star-forming regions, while other areas appear quieter, perhaps depleted by earlier bursts of activity. The overall effect is that of a living ecosystem. Areas of calm next to regions of chaos, all revolving together around the galaxy's nucleus. When astronomers analyze the ring's dynamics, they find even more surprises. The gas moves at tremendous speeds, hundreds of kilometers per second, as it orbits the central bulge. These fast motions generate strong magnetic fields and shock waves that ripple through the dust, further shaping its appearance. In some Hubble images, you can actually see fine thread-like structures running tangentially along the ring, marking where the gas has been stretched and twisted by these forces. It's a reminder that galaxies are not static pictures, but dynamic systems in constant motion. Temperature also plays a key role in the ring's behavior. The coldest regions, where star formation has yet to begin, emit faintly in radio wavelengths but are invisible in optical light. Slightly warmer areas, where dust grains absorb and re-radiate starlight, glow brightly in the infrared. Instruments like the Spitzer Space Telescope and the James Webb Space Telescope can detect this thermal emission, revealing details hidden to optical telescopes. Webb's infrared sensitivity has recently allowed astronomers to study the chemical makeup of the ring, finding that it contains complex organic molecules, including carbon-based compounds similar to those seen in the Milky Way's own molecular clouds. One of the most intriguing questions about the dark ring is how long it will last. Star formation consumes molecular gas over time, and unless more gas is supplied from the galaxy's outskirts or neighboring systems, the ring will eventually thin out. But for now, it's still going strong. The balance between turbulence, rotation, and gravity keeps feeding the process, maintaining the ring's structure for hundreds of millions of years. To visualize the dark ring's role within the Black-Eye galaxy, imagine a wheel spinning in space. The golden bulge at the center is the hub, glowing with ancient stars. The spiral arms are like the spokes, extending outward. And the dark ring is a band of dense material wrapped around the hub, where new stars are constantly being forged. Every orbit, the ring churns and stirs, recycling its gas into new generations of light. The sheer contrast between the dark ring and the luminous center has made M64 one of the most photographed galaxies in the northern sky. Amateur and professional astrophotographers alike target it because of its unique appearance. With long exposures and careful image processing, they can bring out the subtle structure of the dust lane, its clumps, ridges, and tendrils, along with the faint glow of the inner spiral arms. What appears as a smooth, shadowy band in small telescopes turns into an intricate web of filaments under the gaze of large observatories. But beyond its beauty, the dark ring of M64 is scientifically valuable because it helps astronomers understand how galaxies recycle their material. In most spiral galaxies, gas and dust are gradually used up as stars form, but in M64, the counter-rotating motion and resulting shocks seem to sustain the process longer. It's as though the galaxy found a way to keep its star-forming engine running more efficiently. Studying it could offer clues to how galaxies maintain star formation over billions of years without exhausting their resources. The environment within the ring is extreme. The pressure of gas is high, and the radiation from newly formed stars continuously heats and disrupts the surrounding material. Yet somehow, the ring maintains a balance, a self-regulating mechanism. When star formation becomes too intense, supernova explosions and stellar winds push gas outward, reducing the density and slowing the process. When activity drops, gravity causes gas to fall back inward, reigniting new bursts of star formation. This feedback loop keeps the ring alive, oscillating between calm and chaos. Astronomers using ALMA, the Atacama Large Millimeter Submillimeter Array, have observed fine details of this process. They've detected compact, high-density clumps within the ring, each a few dozen light-years across, that appear to be the seeds of new star clusters. These clumps show strong signs of turbulence and rotation, evidence of the violent forces shaping them. In some cases, jets of ionized gas can be seen shooting outward from the cores of these regions, marking the birth of massive stars. Even more fascinating are the subtle color differences across the ring. In multi-wavelength images, one side of the ring glows slightly redder than the other, indicating differences in dust composition and temperature. This asymmetry might be caused by uneven mixing of material from the past galactic merger, or by gravitational interactions that still ripple through the system. It's a visual reminder that the Black-Eye galaxy's dark ring is not a static structure. It's the visible record of the galaxy's turbulent history and ongoing transformation. Infrared spectroscopy, for example, allows scientists to identify specific molecules in the dust and gas. They've detected carbon monoxide, ammonia, and traces of formaldehyde, all markers of dense cold molecular clouds. These findings connect the processes happening in M64's ring to the same chemistry found in our own Milky Way's star-forming regions, such as the Orion Nebula. In a way, studying the Black Eye Galaxy's dark ring gives us a glimpse into our galaxy's own distant past. The dark ring's depth is also remarkable. Estimates suggest it extends several thousand light-years thick, with the densest regions concentrated near the midplane of the galaxy. Within that thickness, countless layers of gas and dust overlap, each at slightly different velocities. Radio maps show that the ring is not perfectly uniform, but slightly warped, perhaps another lingering effect of the ancient collision that gave birth to it. What's extraordinary is how much energy this structure holds. Although composed of cold gas by astronomical standards, the total kinetic energy of the ring's motion is enormous, enough to power thousands of supernova explosions. This energy is constantly redistributed through shocks, radiation, and turbulence, making the ring one of the most active environments in the galaxy. The central black hole, the quiet powerhouse of the Black Eye Galaxy. At the very heart of the Black Eye Galaxy lies a region of unimaginable gravity, a supermassive black hole roughly 2 million times the mass of the Sun. Every major galaxy we've ever studied seems to hide one, and M64 is no exception. But unlike the monstrous quasars that blaze across the cosmos, the black hole at the center of the Black Eye Galaxy is calm, silent, and patient. It doesn't roar with the energy of an active nucleus. It whispers. Yet even in that quiet state, its invisible hand shapes everything around it, from the motion of nearby stars to the evolution of the galaxy's luminous core. The presence of a central black hole in M64 wasn't discovered immediately. For much of the 20th century, astronomers could only speculate. They knew the galaxy's bright bulge contained millions of tightly packed stars, and that their collective gravity had to be enormous. But it wasn't until advances in spectroscopy and high-resolution imaging that the true mass hidden in the galaxy's heart began to emerge. To detect a black hole that emits little to no light, astronomers rely on motion, the way nearby stars and gas behave under its pull. Imagine watching leaves swirling around a hidden drain in a pond. Even if you can't see the drain itself, the pattern of movement gives it away. In the same way, the stars near the core of M64 move faster than gravity from visible matter alone can explain. By measuring those speeds, the so-called stellar velocity dispersion, scientists can calculate how much unseen mass must be there. The answer for the Black Eye Galaxy points to a black hole weighing roughly 2 million suns. That's relatively modest by galactic standards. Some giant ellipticals harbor black holes with masses of billions of suns, while our own Milky Way's central black hole, Sagittarius A*, weighs about 4 million. But in the case of M64, the smaller mass matches its overall scale. The galaxy itself is roughly half the size of the Milky Way, and the relationship between a galaxy's bulge and its central black hole, known as the M-sigma relation, fits perfectly here. In simple terms, the more massive and tightly packed a galaxy's central region is, the heavier its black hole tends to be. M64 sits comfortably on that curve. What's striking about the Black Eye Galaxy's black hole isn't its size, but its quietness. Astronomers call such objects low-luminosity active galactic nuclei, or even inactive nuclei, depending on the energy they emit. In M64's case, the black hole appears to be accreting, pulling in surrounding gas and dust at an extremely low rate. It's not currently feeding in a dramatic way. That's why the galaxy's center doesn't shine with the high-energy radiation typical of quasars or Seyfert galaxies. Instead, it's subdued, emitting only faint radio and X-ray signals detectable with sensitive instruments. To put this into perspective, when a supermassive black hole actively feeds, the energy released from infalling matter can outshine the entire galaxy. As gas spirals inward, friction heats it to millions of degrees, generating intense light before the matter finally crosses the event horizon. But in the Black Eye galaxy, this process is running in slow motion. The central black hole isn't starved, it's simply choosing to sip rather than devour. Why is it so quiet? The answer lies partly in its environment. Although the galaxy's dark dust ring is packed with cold molecular gas, much of that material orbits too far from the center to fall directly into the black hole. The inner regions near the nucleus contain mostly older stars and relatively little free gas. Without a steady supply of infalling material, the black hole has nothing substantial to feed on. It exists in a kind of cosmic dormancy, massive, powerful, but dormant until disturbed. Even in this quiet state, the black hole influences its surroundings in subtle yet measurable ways. The stars near the galaxy's core move in tight, rapid orbits, their paths shaped by the gravitational pull of the central mass. Gas clouds that stray too close are accelerated, stretched, and heated, sometimes emitting faint X-rays as they spiral inward. The energy output may be small compared to an active galaxy, but it's enough to reveal the black hole's presence. Astronomers use several methods to probe this hidden powerhouse. One of the most direct is spectroscopic mapping, measuring how light from the galaxy's nucleus is shifted by motion. Using instruments on large observatories like the Hubble Space Telescope's Space Telescope Imaging Spectrograph (STIS), scientists can record the Doppler shifts of emission lines from gas orbiting close to the center. On one side of the nucleus, light is slightly blue shifted as the gas moves toward us. On the other side, it's red shifted as it moves away. From these shifts, they can calculate orbital speeds, sometimes hundreds of kilometers per second, and from that, estimate the enclosed mass. For M64, those measurements clearly point to a massive compact object, far too dense to be anything other than a black hole. The inferred size of this invisible region is smaller than our solar system, yet it holds 2 million solar masses. No cluster of stars or dense cloud could survive in such a configuration without collapsing. Gravity alone confirms the black hole's existence. Another technique involves studying X-ray emissions. Even when accretion is weak, some material still falls inward, producing hot plasma that glows faintly in X-rays. Observations from NASA's Chandra X-ray Observatory and ESA's XMM Newton have detected low-level X-ray activity from the core of the Black Eye galaxy, consistent with a dormant or starving black hole. The spectrum suggests a temperature of millions of degrees, typical for gas in the innermost accretion zones of black holes, though far dimmer than in an active quasar. In some galaxies, even a quiet black hole can occasionally flare up. If a star wanders too close, it can be torn apart by tidal forces in what's known as a tidal disruption event. The debris from the shredded star briefly feeds the black hole, producing a burst of light. So far, no such event has been recorded in M64, but astronomers keep watch. If one were to occur, it would light up the galaxy's core for months or even years, briefly revealing the black hole's hunger before fading back into silence. What's fascinating is how perfectly balanced the system seems. The black hole's inactivity may actually help preserve the galaxy's ordered structure. In galaxies where the central black hole is highly active, the energy it releases can blow gas outward in vast jets, disrupting star formation and reshaping the disk. In M64, no such chaos is occurring. The dust ring, the spiral arms, and the stellar bulge remain stable. The galaxy's quiet nucleus may be the reason its features have remained so intact since its ancient merger. There's another intriguing layer to this story: the possibility that the black hole itself was influenced by that past collision. When the smaller galaxy merged with M64, its own central black hole, if it had one, might have sunk toward the center and merged with M64S. Such mergers release immense amounts of gravitational energy, though the event would have taken place billions of years ago, long before modern instruments could have recorded it. The result would be a slightly more massive, but now settled, black hole, the one we observe today. In fact, this might help explain why the nucleus is quiet. After such a merger, the central region could have expelled much of its gas or stabilized its orbits, leaving the black hole without a steady inflow of material. Over time, with less fuel to consume, it would naturally dim. What remains is a relic, a powerful gravitational anchor surrounded by the slow dance of aging stars. Even without active feeding, the black hole continues to affect the motions of stars within several light-years of the center. These inner stars form what astronomers call the nuclear stellar cluster, a dense grouping that orbits the black hole at incredible speeds. In galaxies like M64, these clusters often act as buffers between the black hole and the larger bulge, helping to regulate how material flows inward. High-resolution imaging has even revealed slight asymmetries in the brightness of the central region, possibly caused by gravitational interactions between the black hole and nearby stars. Measuring such subtle details is no small feat. The core of M64 spans only a few arcseconds when viewed from Earth, the size of a grain of sand seen from several kilometers away. To resolve it, astronomers rely on space telescopes and advanced adaptive optics systems that correct for Earth's atmospheric distortion. The results show a nucleus with a smooth, round profile and a slight central brightening, the telltale glow of a low-level active galactic nucleus. At radio wavelengths, instruments like the Very Large Array, VLA, detect faint emissions consistent with synchrotron radiation, the type produced by electrons spiraling around magnetic fields near a black hole. These weak signals provide another piece of evidence for ongoing, though minimal, accretion activity. Combined with X-ray data, they paint a picture of a black hole that is not completely asleep, but idling in a low-energy state. This low-luminosity phase may not last forever. Galaxies evolve on timescales of hundreds of millions of years, and conditions can change. If a new stream of gas from the outer disk or from the dark ring eventually drifts inward, it could awaken the black hole, triggering a fresh burst of activity. For now, though, M64's central engine remains calm, a sleeping giant resting at the heart of a galaxy that bears its signature. The idea of a quiet black hole might seem contradictory, but in astrophysics, stillness can be just as revealing as violence. By studying galaxies like M64, researchers learn what happens between the outbursts, the long, stable periods when the galaxy and its black hole coexist peacefully. These quiescent phases make up the majority of a black hole's life. Only occasionally, when conditions align, does it flare into brilliance. It's possible that the black-eye galaxy's tranquil nucleus represents a mature stage of galactic evolution. The violent youth of mergers and starbursts is over, replaced by balance. The spiral arms continue to form stars at a moderate rate. The dust ring remains active but contained, and the central black hole quietly anchors the system, its gravity holding the inner galaxy together. In this way, the black hole acts as both the stabilizer and silent overseer of its cosmic domain. What makes this particularly fascinating is that the behavior of M64's black hole offers a glimpse into the potential future of our own Milky Way. Sagittarius A*, too, is mostly dormant, feeding at an extremely low rate. It shines faintly in radio and X-rays, just like M64's core. Billions of years from now, when our galaxy's star formation slows and gas supplies thin out, it may look much like the Black-Eye galaxy. Peaceful on the surface, yet with an immense gravitational heart beating quietly within. Astronomers are always looking for ways to measure black holes more precisely, and M64 provides an excellent laboratory. Because it's relatively close, only about 24 million light-years away, instruments like the Event Horizon Telescope, EHT, could, in theory, one day detect radio structures close to its core, just as they have done for the black holes in M87 and the Milky Way. Even if the black hole in M64 is smaller and less active, future technology could reveal the faint glow of its accretion disk or the pattern of polarized light near its event horizon. Understanding such a quiet black hole also helps refine theoretical models. In astrophysics, low-luminosity black holes like M64's test our understanding of how accretion physics works when material flows at a trickle rather than a flood. In these conditions, the energy released comes mostly from slow-moving, radiatively inefficient flows, meaning much of the gas's potential energy is swallowed rather than radiated. Observations of M64 help confirm these models, providing a natural bridge between active galactic nuclei and fully dormant black holes. There's also a precision in how this central mass interacts with the rest of the galaxy's structure. The spiral arms, the dust ring, and the outer disk all revolve under its gravitational influence. Even though the black hole occupies a tiny fraction of the galaxy's total size, its presence ensures that everything stays balanced. Without it, the central bulge might not hold together so tightly. The orbits of stars near the core could drift apart. In a sense, this quiet black hole is the anchor of the entire galactic system, unseen but indispensable. If we could somehow observe the region directly, the view would defy comprehension. Near the event horizon, space itself curves sharply inward. Any gas or dust that ventures too close is stretched and heated, glowing briefly before disappearing forever. Yet from the outside, time appears to slow as matter falls in, freezing just above the horizon in a ghostly red light. The surrounding stars orbit in graceful ellipses, their paths warped by gravity so extreme that even light bends. The galactic collision that changed everything. What sets Messier 64 apart from most spiral galaxies isn't just the dark ring of dust wrapped around its bright core, but the fact that the galaxy's gas disks are actually rotating in opposite directions. This isn't just a minor quirk. It's a cosmic contradiction written across tens of thousands of light years. This strange counter-rotation has turned M64 into one of the most intriguing subjects in extragalactic astronomy. A natural laboratory for understanding what happens when galaxies collide and merge. When astronomers first began mapping the motion of stars and gas within M64, they expected it to behave like a normal spiral, everything orbiting the center in the same direction, following the orderly rotation of the galactic disk. But when radio telescopes began to study the movement of neutral hydrogen gas, known as HI, something unexpected appeared. The inner region of the galaxy, up to about 3,000 light-years from the center, showed gas moving one way, while the outer region, extending far beyond 40,000 light-years, rotated in the exact opposite direction. This was not a measurement error. Multiple observatories confirmed it, including the Very Large Array, VLA, in New Mexico, and later the Atacama Large Millimeter Submillimeter Array, ALMA, in Chile. Each one showed the same result. The gas clouds within M64's disk were counter-rotating. To visualize it, imagine a record player spinning one direction, but the outer edge suddenly reversing and spinning back the other way. That's what's happening across tens of thousands of light years in M64. This discovery stunned astronomers. Counter-rotation on such a scale meant something dramatic had happened in the galaxy's past. Galaxies don't just wake up one day with part of their gas spinning in reverse. The only realistic explanation was that M64 had experienced a merger, a collision with another, smaller galaxy that carried its own angular momentum in a different direction. The evidence for this merger is strong. The outer gas disk, made primarily of hydrogen, doesn't share the same metallicity or chemical enrichment as the inner regions. It's slightly more pristine, meaning it likely came from a smaller, younger, gas-rich galaxy that hadn't gone through as many cycles of starbirth and death. This is one of the signatures astronomers look for when identifying remnants of galactic mergers. Simulations of galactic interactions also match what's seen in M64. When a smaller galaxy merges into a larger spiral from the opposite direction, the captured gas can retain its original spin for billions of years. Over time, this leads to exactly what M64 shows today: two nested disks rotating against each other, separated by a zone of high turbulence and star formation. In M64, that turbulent zone is not theoretical. It's visible in the dust lane itself. The dark band that gives the galaxy its black eye appearance is the frontier where the counter-rotating gases meet. This collision between two massive streams of interstellar gas creates shock fronts, compressing the material and triggering intense bursts of star formation. Within this ring, astronomers have identified clusters of hot young stars and glowing H2 regions, signs that the dust lane isn't just dark, it's alive with activity. It's a kind of cosmic traffic jam. As the two disks shear past one another, molecular clouds collide. Their internal pressures rise, and gravity takes over, collapsing the gas into new stars. What we see as a dark, bruised band around the core is, in reality, a construction zone for stellar nurseries. Evidence of ongoing galactic evolution. The two disks differ not just in rotation, but also in scale. The inner disk, about 3,000 light-years across, is made mostly of stars and ionized gas, older, settled material that likely belongs to the original M64 before the merger. The outer disk, by contrast, stretches beyond 40,000 light-years and is dominated by neutral hydrogen and cold molecular gas. This is the remnant of the intruder galaxy, the system that crashed into M64 roughly 1 billion years ago and changed its motion forever. Radio observations have been crucial in identifying these differences. Using the VLA, astronomers can map the hydrogen gas in radio wavelengths, detecting its motion through Doppler shifts. When gas moves toward us, its radio waves are slightly compressed, a blue shift. When it moves away, the waves stretch, creating a red shift. By mapping these shifts across the galaxy, researchers created a detailed velocity field that revealed the two opposing spins. ALMA has taken that even further by observing carbon monoxide, CO, emissions, which trace the denser molecular gas that forms stars. These observations show that the molecular gas follows the same pattern, counter-rotating flows that overlap near the dust lane, exactly where star formation rates are highest. Optical telescopes add another layer of information. The Hubble Space Telescope and the Sloan Digital Sky Survey, SDSS, have provided high-resolution images that show how the dust and star-forming regions are arranged. When combined with spectroscopic data, these observations confirm that the central bulge and inner disk rotate in one direction, while the outer spiral arms swing the other way. The visual beauty of M64 is, therefore, directly tied to its chaotic internal physics. What makes this system so fascinating to astronomers is that counter-rotation on this scale is relatively rare. In some galaxies, scientists have found smaller counter-rotating components, for example, a central gas ring spinning backward compared to the stars. But in M64, the reversed rotation involves entire layers of gas extending tens of thousands of light-years. It's one of the clearest examples of large-scale counter-rotation ever observed. Studying M64 gives insight into how galaxies grow and evolve. Collisions and mergers are not rare events in the universe. They're part of how galaxies build up mass over time. The Milky Way itself has swallowed smaller galaxies in the past and will eventually merge with Andromeda in about 4 billion years. By looking at M64, astronomers get a preview of how such interactions can alter rotation, structure, and star formation long after the collision itself. One of the lingering mysteries is how long the counter-rotation can persist. Simulations suggest that over billions of years, friction and gravitational mixing will gradually align the gas motions. But in M64, the opposite spins still appear distinct, meaning the merger was relatively recent in cosmic terms. This also implies that the galaxy is still dynamically settling, still working to find balance after the upheaval. The evidence of turbulence where the disks meet is another indicator of its unsettled nature. When gas clouds with opposite spins collide, they produce strong shear forces. These forces not only trigger star formation, but can also lead to shocks that heat some of the gas, disrupting stable star-forming regions. The combination of compression and chaos creates a patchwork of calm and violent zones across the dust lane. Interestingly, despite this complex history, M64's overall spiral structure remains well defined. The bright inner disk maintains symmetrical spiral arms, while the outer disk shows faint extensions and subtle distortions. Signs of gravitational warping from the past encounter. This balance of order and disturbance makes the galaxy both visually striking and scientifically rich. Astronomers continue to use multi-wavelength observations to map out more details. Infrared data from the Spitzer Space Telescope shows where dust is warm and star formation is active. Ultraviolet images from Galactic reveal clusters of hot young stars that trace recent bursts of formation. Together, these datasets paint a picture of a galaxy that, though scarred, is still thriving. The black eye itself, the dark band of dust, may well be the visible scar left by the merger. It's a fossil record written in dust and light, a lingering mark of the smaller galaxy that merged and dissolved into M64's structure. That merger didn't destroy the spiral, it reshaped it, leaving behind one of the most photogenic and scientifically fascinating galaxies in the night sky. Even now, astronomers are refining the timeline of the event. The best models suggest that the smaller companion galaxy was about 1/10 the mass of M64 and was rich in gas. When it was drawn in by M64's gravity about 1 billion years ago, tidal forces stripped it apart. Most of its stars were absorbed into the outer halo, while its gas spread across the disk, spinning in the opposite direction of the original galaxy's rotation. That reverse motion continues to fuel the turbulence we see today. Every time gas from the outer disk interacts with the inner region, more star formation ignites, keeping the dust lane active. The galaxy has essentially recycled the debris of its past collision into new generations of stars. Spectroscopic data from the Sloan Digital Sky Survey has even allowed astronomers to estimate the relative ages of the two components. The inner disk, composed mainly of older stars, shows signs of having formed billions of years before the merger. The outer disk, however, contains younger populations, consistent with the idea that the gas from the smaller galaxy only began forming new stars after the merger event. At optical wavelengths, the contrast between these regions is striking. The inner bulge glows with a yellowish hue typical of ancient stars, while the outer regions are speckled with blue, light from newborn stars that are only a few million years old. Star formation and galactic ecology. Astronomers have long known that star formation begins in clouds of molecular gas, primarily hydrogen molecules, H2, mixed with traces of carbon monoxide, CO, and other elements. In M64, the dark lane circling the core is rich with these ingredients. Observations of CO emission lines, the spectral fingerprints that reveal where cold molecular gas lies, show strong concentrations along this dust lane. This means it's packed with dense clouds that are the perfect conditions for starbirth. Using instruments like the Atacama Large Millimeter Submillimeter Array, ALMA, astronomers have mapped these CO emissions in fine detail. What they found is that the dust lane isn't just a uniform band. It's a complex network of filaments, knots, and dense pockets. Regions where the gas density reaches thousands of particles per cubic centimeter, enough for gravity to take over. As these clouds collapse, their centers heat up, forming protostars that eventually ignite into main sequence stars. The Galaxy Evolution Explorer, GALEX, which observes in the ultraviolet UV spectrum, added another piece of the puzzle. Ultraviolet light is emitted by young hot stars, massive short-lived stars that burn intensely before exploding as supernovae. GALEX images show bright UV streaks along the same dust lane where the CO emissions peak, confirming that this is where the galaxy's most recent star formation is concentrated. This alignment, CO emission tracing cold gas, UV emission tracing hot young stars, gives astronomers a time sequence of star formation in action. In M64, the dust lane acts as both a nursery and a conveyor belt. Gas flows inward, gets compressed by the counter-rotating disks, and collapses into stars. Then, the newborn stars energize their surroundings with radiation and stellar winds, shaping the next generation of star-forming clouds. The balance between compression and feedback is delicate. Too much turbulence and the gas disperses before stars can form. Too little and the gas cools without triggering collapse. In the Black Eye galaxy, the collision that created the counter-rotation provided exactly the kind of turbulence needed to stimulate sustained star formation. The result is a galaxy that billions of years after its merger is still building stars faster than many other galaxies of similar size and age. What's remarkable is how efficiently this process happens within the dark lane. The inner and outer disks of M64 rotate in opposite directions, and where they meet, their relative motion generates shear, layers of gas sliding past each other at different speeds. This shear compresses the molecular gas in localized zones, driving it into collapse. Astronomers have identified numerous such zones, compact star-forming regions marked by intense H emission, the telltale red glow of hydrogen gas ionized by newborn stars. Each of these glowing regions represents a miniature stellar cluster, a collection of young stars no more than a few million years old. Many of these clusters are embedded in thick dust, visible only in infrared wavelengths. The Spitzer Space Telescope's infrared maps of M64 reveal these embedded sources glowing through the dust, confirming that star formation is happening deep within the obscured parts of the lane, the very regions that make the galaxy appear bruised and shadowed in optical light. From an astrophysical standpoint, the dust lane of M64 can be seen as a feedback loop. The counter-rotation drives turbulence. Turbulence creates dense pockets of gas, and those pockets give birth to stars. The newborn stars then stir the surrounding gas with their energy, triggering more collapse in adjacent regions. It's a self-sustaining process, constantly renewing itself as long as gas continues to flow through the region. If we look beyond the dust lane and examine the galaxy as a whole, M64 presents a layered story of stellar populations. The central core, the bulge, glows with the golden hue of ancient stars, primarily yellow and red giants that are between 9 and 12 billion years old. These stars formed early in the galaxy's history, long before the merger that caused its famous counter-rotation. Their light dominates the inner few thousand light-years, giving the core its warm appearance even through the surrounding dust. Surrounding that core is the ring, the region defined by the dust lane and its immediate surroundings. Here, the population of stars is mixed. Some are old survivors from the original galaxy, while others are newborns formed after the merger. This blend gives the ring a more varied color profile, with blue-white highlights from young, massive stars scattered among the golden glow of older populations. Spectroscopic studies of these regions reveal that many stars in the ring are only a few million years old, some possibly younger than 1 million. This contrast between old and new is what makes M64 such a compelling object of study. In a single image, you can see nearly the entire life cycle of stellar evolution. Ancient stars near the center, middle-aged stars in the intermediate regions, and young stars blazing along the dust lane. It's a living cross-section of galactic history, frozen in one spiral form. When astronomers compare M64 to other ringed galaxies, interesting similarities emerge. Galaxies like NGC 7742 or NGC 7217 also show prominent rings of star formation, and in some cases, signs of past mergers or counter-rotation. These ringed spirals often form when gas is driven into circular orbits by gravitational resonances or mergers, exactly what seems to have happened in M64. The dark lane of M64 may therefore be part of a larger class of ring structures that trace the aftermath of galactic interactions. But M64's ring is unique in its contrast. While galaxies like NGC 7742 have bright, luminous star-forming rings, M64's ring is wrapped in dust. That dust blocks visible light, making the ring appear dark even though it's full of activity. It's a reminder that the visual darkness we see isn't emptiness. It's the opposite, the densest, richest parts of the galaxy, teeming with gas, dust, and new life. The mixture of populations also tells astronomers about how star formation has proceeded since the merger. The ratio of young to old stars in different parts of the ring suggests that star formation hasn't been constant. It comes in waves. When the two gas disks first began to interact, the compression was strongest, leading to a burst of star formation. As the gas redistributed and settled, the rate slowed, only to rise again as new shocks and turbulence formed. Even now, small pockets of active star formation continue to appear along the lane. The stellar populations also vary in metallicity, the abundance of elements heavier than hydrogen and helium. Stars in the core are metal-rich, reflecting billions of years of enrichment from previous generations of stars. In contrast, the stars in the outer regions and the dust lane have lower metallicities, consistent with gas that originated in the smaller, less evolved companion galaxy that merged with M64. This chemical fingerprint further supports the idea that the merger brought in new material from outside, fueling fresh waves of star birth. The interplay between these populations creates a kind of internal diversity, an ecosystem of stars at every stage of evolution, from newly ignited blue giants to fading red giants and white dwarfs. The distribution of these populations gives the galaxy its layered texture when viewed in multi-wavelength images: infrared for old stars, visible light for middle-aged ones, ultraviolet for the youngest. Together, they tell a continuous story of formation, aging, and renewal. Star formation in a calm spiral galaxy follows a relatively predictable pattern. Gas cools, collapses, and forms stars, which then slowly drift into the galactic arms. But M64 isn't calm. The counter-rotation created by its ancient merger means that gas clouds in different layers move in opposite directions, colliding and compressing each other. This changes everything about how stars form and evolve inside the galaxy. When gas clouds moving in opposite directions meet, the relative velocity between them can be several tens of kilometers per second. These collisions generate shock waves that ripple through the interstellar medium, raising local pressure and density. This accelerates the collapse of some clouds, increasing the efficiency of star formation, but also tears others apart. It's a high-stakes environment where the fate of a gas cloud depends on the precise balance of compression and turbulence. Computer simulations of counter-rotating galaxies show that this process can enhance star formation efficiency by factors of 2 or 3 compared to isolated galaxies. That matches what's seen in M64. Its rate of star formation, especially in the dust lane, is higher than one would expect for a galaxy of its size. Once stars are born, their evolution further shapes the environment. Massive stars, those more than 8 times the mass of the Sun, live fast and die young. Within a few million years, they explode as supernova, injecting energy, radiation, and heavy elements into their surroundings. This feedback disrupts nearby gas clouds, halting star formation locally but enriching the interstellar medium with new materials that future stars can incorporate. In M64, the feedback cycle is particularly intense. The density of massive, short-lived stars in the dust lane means that supernovae occur frequently, creating overlapping shock waves. These shocks carve out cavities in the gas, forming bubbles and filaments that are visible in high-resolution Hubble images. In some regions, these bubbles merge into superbubbles, vast cavities tens of light-years wide, bordered by dense shells where new stars are triggered to form. Stellar winds from young hot stars also play a major role. These winds push on the surrounding gas, sculpting the dust lane into arcs and pillars. Observations in infrared and radio wavelengths show that the structure of the dust is far from uniform. It's constantly being reshaped by the forces within it. Each new generation of stars influences the next, creating a continuous cycle of formation, destruction, and renewal. The counter-rotation may also influence how long star formation can continue. In typical galaxies, gas slowly settles into stable orbits, eventually running out of dense material to form stars. But in M64, the constant shearing between the two rotating disks keeps the gas stirred up, preventing it from fully stabilizing. This may prolong the period of active star formation, making the galaxy more productive over longer timescales. Even the supermassive black hole at the galaxy's center could be affected by this complex ecology. Gas funneled inward through the dust lane may occasionally feed the black hole, producing weak but measurable activity in the nucleus. Although M64's central black hole is relatively quiet today, evidence of faint emission suggests it has been intermittently active in the past, possibly triggered by inflows of gas from these same star-forming regions. Astronomers studying M64 often refer to it as an ecological system, not in the biological sense, but in the way its parts interact and depend on one another. The dust lane provides the raw material, the counter-rotation supplies the energy and turbulence, and star formation drives the cycle of enrichment and renewal. Each process feeds into the next, maintaining a kind of dynamic balance that has lasted for hundreds of millions of years. The galaxy's ongoing evolution can be seen in real time, not in human years, but in cosmic terms. Over the next billion years, the counter-rotating gas will likely continue to mix, gradually aligning its motion. Star formation will slowly migrate outward as the inner regions use up their gas. The bright, turbulent dust lane may fade as the galaxy transitions into a quieter phase. The chemical fingerprint. When astronomers look at the Black-Eye Galaxy, M64, they don't just see stars, dust, and light. They also see a signature written in chemistry. Every cloud, every burst of star formation, every swirling arm carries a record of what the galaxy has lived through. That record is locked inside the atoms that make up its stars and gas. And by reading those atoms, scientists can piece together the story of how M64 came to look the way it does today. The strange swirl of counter-rotating gas, the dark ring, and the glowing bulge at the center. To understand this fingerprint, astronomers study something called metallicity. In astronomy, metals doesn't mean iron or steel. It means every element heavier than hydrogen and helium. The first stars born in the early universe were made almost entirely of hydrogen and helium, the lightest elements. When those stars died, often in violent supernova explosions, they created heavier elements like carbon, oxygen, nitrogen, silicon, and iron. These elements then mixed into the next generation of stars. So the more metals a star or gas cloud contains, the more generations of stellar birth and death it's been through. In other words, metallicity acts like a cosmic clock. It tells astronomers how evolved a region of space is. Young galaxies or regions that have recently acquired fresh, unprocessed gas will have lower metallicity, meaning fewer heavy elements. Older, more mature areas, where stars have been born and died for billions of years, will have higher metallicity. When scientists began to measure the metallicity across M64, they found something unusual, a clear difference between the inner and outer regions. The gas and stars closer to the core of the Black-Eye Galaxy are rich in heavy elements, much like the inner regions of our own Milky Way. But as you move outward, especially into the counter-rotating outer disk, the metallicity drops sharply. That means the outer gas has fewer heavy elements, a sign that it didn't originate in the same environment as the core. This observation became one of the strongest pieces of evidence supporting the merger theory. If M64 had always evolved as a single isolated system, the metallicity would gradually decline with radius, as in most spiral galaxies. But it wouldn't show such a sharp contrast. The outer disk's lower metallicity suggests that it came from another galaxy, a smaller, gas-rich one that collided with M64 long ago. That galaxy, being smaller and less evolved, would have had fewer heavy elements. When it merged, it donated its gas to M64's outskirts, setting up the counter-rotating outer ring that astronomers still observe today. To measure this, astronomers used spectroscopy, splitting light from different regions of the galaxy into its component wavelengths. Every element leaves a distinct set of lines in a spectrum, a kind of barcode that reveals what the gas and stars are made of. For instance, oxygen, nitrogen, and sulfur lines are often used to estimate metallicity in star-forming regions. The stronger these emission lines appear relative to hydrogen lines, the more enriched the gas is in heavy elements. Radio telescopes and optical observatories both played a role. The Very Large Telescope, VLT in Chile, and the Keck Observatory in Hawaii have both observed M64, providing high-resolution spectra of its inner and outer disks. These observations show that the gas in the inner disk, the part that rotates with the stars, has metallicities comparable to those of the Milky Way's central regions. In contrast, the outer disk, which rotates the opposite way, has metallicities about 1/3 lower. That may sound small, but in galactic chemistry, that's a huge difference. It tells astronomers that the two regions didn't share the same chemical history. One of the most fascinating clues comes from the study of ionized gas clouds, glowing regions where new stars are being born. In M64, many of these appear along the dark dust lane, where the two disks meet. By examining the light from these H2 regions, astronomers can trace how elements like oxygen and nitrogen vary from the inner ring outward. The results are consistent. The metallicity gradually falls as one moves away from the center, then drops more steeply in the counter-rotating outer gas. This metallicity map paints a vivid picture of what likely happened a billion years ago. Imagine M64 as a mature spiral galaxy, already rich in heavy elements from billions of years of star formation. Then a smaller galaxy, lighter, younger, poorer in metals, drifts too close. Its gas is drawn in by gravity, wrapping around M64 and eventually settling into a rotating disk, but in the opposite direction. Over time, this captured gas mixes partially with the existing material, but not completely. The two systems never fully homogenize, leaving behind a chemical and rotational mismatch, the very feature we see today. Another key insight comes from carbon monoxide, CO observations. CO is a good tracer of cold molecular gas, the raw material for star formation. Using instruments like ALMA, the Atacama Large Millimeter Submillimeter Array, astronomers mapped CO emission across M64. They found that the inner regions have a higher CO to H2 ratio, again consistent with more metal-rich gas, where molecules form more easily on dust grains. The outer regions, in contrast, show weaker CO signals relative to their hydrogen content, indicating that the gas is not only poorer in metals, but also less efficient at forming molecular clouds. This chemical imbalance affects how stars form. In metal-poor gas, cooling is less efficient because metals and dust are key to radiating away heat. That means molecular clouds in the outer disk may stay warmer and less dense, leading to slower star formation. Inside the dark ring, however, where metal-rich and metal-poor gas collide and compress, the conditions are just right for bursts of star formation. The friction between the two flows creates shock waves, squeezing the gas and igniting clusters of new stars, a process visible in ultraviolet and infrared images of M64. The chemistry also reveals something about time. By comparing metallicity gradients with models of galactic evolution, astronomers estimate that the merger must have happened about 1 billion years ago. Recent enough that the two disks haven't fully mixed, but long enough that the captured gas has formed several generations of stars. The younger stars in the outer ring show intermediate metallicities, slightly higher than the original infalling gas, because they've already been enriched by earlier supernova explosions. Even the dust composition tells a story. Infrared observations from NASA's Spitzer Space Telescope and Herschel Space Observatory show variations in dust grain properties across M64. In the inner regions, the dust has a higher content of silicates and carbon-rich compounds, typical of material ejected from old stars. In the outer disk, the dust appears more primitive, less processed, with simpler molecules and fewer complex organics. That fits perfectly with the idea that the outer gas came from a smaller, chemically younger galaxy. Spectroscopic data from the Sloan Digital Sky Survey, SDSS, adds another layer. By analyzing the light from hundreds of points across M64, SDSS confirmed that the metallicity distribution isn't symmetrical. One side of the outer ring shows slightly higher enrichment, possibly where mixing with the inner disk has been more intense. This unevenness supports the view that the merger was not a gentle head-on event, but an off-center collision, with the smaller galaxy entering from one side and leaving its material unevenly distributed. What makes the chemical story of M64 so valuable is that it provides direct, measurable evidence of how galaxies grow. While we often think of galactic mergers as violent and chaotic, in reality, many are slow, drawn-out processes that leave behind layered signatures in motion, in light, and in chemistry. The Black Eye Galaxy shows this in exceptional detail. Its inner stars tell the story of an ancient spiral, evolved and metal-rich. Its outer gas whispers of a younger, less experienced companion. And between them, where the two meet, lies a zone of chemical blending, a laboratory for understanding how galaxies recycle and rebuild themselves after a collision. Researchers have also compared M64's chemical patterns with those in other counter-rotating systems. Galaxies like NGC 4550 and NGC 7217 show similar signatures, metallicity drops, younger stellar populations in outer rings, and gas moving in opposite directions. M64 stands out because it's relatively close and bright, allowing scientists to study it in far greater detail. Its well-defined dust lane and two cleanly separated disks make it a near-perfect case study for how mergers redistribute not just motion, but matter itself. Future missions are expected to refine these measurements even further. Instruments aboard the James Webb Space Telescope, JWST, can detect faint infrared emission lines from elements like neon and sulfur, offering a more precise map of how metallicity changes across the Black Eye Galaxy. Astronomers hope to track how newly formed stars in the ring enrich their surroundings over time, watching, in effect, the chemical healing process of a galaxy that once collided with another. The chemical fingerprint also helps astronomers model how the Milky Way might evolve after future mergers. Our galaxy is expected to collide with the Andromeda Galaxy in about 4 billion years. Studying systems like M64 gives scientists a preview of what such an event could leave behind. Multiple rotating disks, chemical imbalances, and new bursts of star formation as the two mix. Even the amount of nitrogen relative to oxygen, something that can be measured with precision spectroscopy, provides clues about the star formation history. In M64's inner regions, higher nitrogen to oxygen ratios suggest that many generations of intermediate mass stars have lived and died there, releasing nitrogen through slow stellar winds. The outer regions, by contrast, have lower ratios, meaning fewer such stars have contributed their chemical products. This fine detail helps scientists reconstruct not only the merger, but also how long each region has been forming stars since that event. Black Eye Galaxy in different wavelengths. When we look at the universe with our eyes alone, we see only a fraction of what is out there. Telescopes that capture light beyond the visible spectrum reveal phenomena invisible to the naked eye. In infrared images, the dust lane transforms from a mere silhouette into a luminous, active region. Dense molecular clouds glow in the infrared as they absorb and re-emit the radiation from newly forming stars. JWST's unprecedented sensitivity allows astronomers to resolve these clouds into individual clumps and filaments, showing where stars are forming and how they are distributed across the lane. Embedded within these clouds are protostars, still shrouded in the gas and dust from which they were born. These stars are invisible in optical light, but glow brightly in infrared, providing a direct view into the heart of stellar nurseries. The optical and infrared combination also helps astronomers map the galaxy's dust content. By comparing the absorption of starlight in visible wavelengths with the infrared emission, researchers can estimate the density and composition of dust grains. In M64, this analysis shows that the dark lane contains a rich mix of silicates, carbonaceous compounds, and molecular gas, the ingredients necessary for ongoing star formation. Observing the galaxy in these two wavelengths simultaneously creates a more complete image. The luminous stars and spiral arms of the core, the shadowy dark ring, and the glowing embedded stars hidden within. Infrared observations further reveal the dynamics of star formation. Dense regions of the dust lane correspond to areas of high infrared emission, indicating that gas is collapsing under gravity to form new stars. Smaller, less dense filaments emit more weakly, suggesting that they are either in earlier stages of collapse or disrupted by turbulence. This spatial differentiation allows astronomers to track the efficiency of star formation along the dark lane. Some regions of M64 are producing stars rapidly, while others appear quiescent, providing a dynamic snapshot of the galaxy's ongoing evolution. Moving beyond light as humans perceive it, radio waves offer another perspective on the black-eye galaxy. Hydrogen, the most abundant element in the universe, emits radiation at a wavelength of 21 centimeters, a hallmark of neutral hydrogen, HI. Using radio telescopes, astronomers can map this HI emission to trace the distribution and motion of cold neutral gas across M64. High mapping of the galaxy has been crucial in understanding its counter-rotating disks. Radio observations reveal that the inner disk, consisting of stars and gas, rotates in one direction, while the outer disk of neutral hydrogen moves oppositely. These counter-rotating flows extend tens of thousands of light-years, and the interface between them is a region of intense shear and turbulence. Without radio data, this key feature of M64's dynamic structure would remain invisible, as neutral hydrogen emits no visible light. High-resolution radio surveys also show extended gas structures beyond the optical disk. These faint diffuse regions indicate that M64 is still surrounded by a reservoir of gas from its past merger. This gas likely feeds ongoing star formation along the dust lane, replenishing the galaxy's supply of molecular clouds. The outer gas disk is less chemically enriched than the inner disk, reinforcing the idea that it originated from a smaller, metal-poor companion galaxy. Radio observations can also detect molecular gas using CO emission lines. Molecular hydrogen, the fuel for star formation, is difficult to observe directly, but CO acts as a tracer. CO mapping shows where the densest star-forming clouds lie, confirming that the dark ring is indeed a hotbed of stellar birth. Radio observations combined with optical and infrared data provide a comprehensive picture of both the gas distribution and the regions actively producing stars. Beyond mapping gas, radio telescopes can probe magnetic fields. By measuring polarized radio emission, astronomers detect distortions in M64's magnetic field caused by turbulence and shear in the counter-rotating disks. Magnetic fields influence the collapse of gas clouds and the formation of stars, adding another layer of complexity to the galaxy's ecology. Observations suggest that magnetic lines are stretched and twisted along the dust lane, guiding gas flows and potentially affecting the rate and location of star formation. Microwave observations add further detail. While primarily used in cosmic background studies, sensitive microwave measurements of galaxies can detect cold dust emission and certain molecular transitions. These observations complement radio and infrared data, helping astronomers estimate the total mass of gas and dust, the temperature of molecular clouds, and the distribution of different chemical components. In M64, microwaves confirm the presence of cold molecular gas in the outer disk and the dark lane, supporting the view that the galaxy is still actively forming stars long after its merger. Ultraviolet, UV observations offer another perspective. UV light is emitted predominantly by young massive stars, hot O and B types with lifespans of only a few million years. Observatories like Galactic have mapped M64 in ultraviolet, revealing the spatial distribution of its youngest stellar population. In these images, the dark lane lights up along its full extent, confirming that the dust ring is far from dormant. Young stars are embedded in the dense molecular clouds, producing intense UV radiation that ionizes surrounding hydrogen gas, forming the familiar H2 regions detected in optical spectroscopy. UV observations also allow astronomers to track recent star formation history. By measuring the intensity and distribution of UV light, scientists can estimate star formation rates across the galaxy. In M64, UV imaging shows that the majority of new stars are concentrated in the dust lane, with some pockets extending into the inner and outer disk. This pattern aligns with theoretical models of star formation, driven by shear between counter-rotating gas disks, demonstrating how dynamics and chemistry work together to shape the stellar population. X-ray observations provide yet another, more extreme view. X-rays are produced by very high-energy phenomena, such as supernova remnants, accreting neutron stars or black holes, and hot gas heated to millions of degrees. In M64, X-ray imaging reveals scattered sources in the central region and along the dust lane. Some of these X-ray emissions come from supernova remnants, the explosive deaths of massive stars formed in the recent star-forming episodes. Others may trace low-level activity from the galaxy's central supermassive black hole, though M64's nucleus is considered relatively quiet compared to active galactic nuclei, AGN. Multi-wavelength synthesis allows astronomers to build three-dimensional models of M64, mapping gas, dust, stars, and magnetic fields in unprecedented detail. Optical light outlines the stars visible to humans. Infrared penetrates the dust to reveal embedded stars. Radio traces the cold gas that fuels star formation. UV pinpoints young stars. X-rays mark the most energetic events. Such multi-wavelength models reveal the complex ecology of the galaxy. The gas, dust, stars, and magnetic fields are not independent. They are interlinked. Gas compression, turbulence from counter-rotation, radiation from young stars, and magnetic field lines all interact to regulate star formation. These processes leave observable signatures in every part of the spectrum. Without a multi-wavelength approach, the story of the Black-Eye Galaxy would be incomplete. 3D modeling allows astronomers to simulate gas flows and star formation with remarkable precision. By feeding data from different wavelengths into hydrodynamic simulations, scientists can recreate the counter-rotating disks, the turbulence at the interface, and the dense star-forming clouds of the dark lane. The simulations match observations closely, confirming the key role of the merger in shaping the galaxy. Polarization data, obtained in radio and infrared wavelengths, reveal how magnetic fields guide gas flows. When combined with the X-ray map of supernova remnants, astronomers can see how feedback from stellar deaths interacts with magnetic structures to influence the next generation of stars. The synthesis also helps identify where star formation is likely to occur in the future. Cold gas in the outer disk, observed in HI and CO lines, may flow inward along spiral arms, adding fuel to the dark lane. Infrared imaging suggests that some molecular clouds are just beginning to collapse. UV and optical light reveal the stars that have already formed, while X-rays show how supernova energy might trigger further star formation or disperse clouds. Multi-wavelength studies also highlight subtleties invisible in any single view. For instance, the dust lane is dark in optical light but bright in infrared. The outer disk appears faint in visible light but shows rich HI emission in radio. The central core emits strongly in optical and infrared, while X-ray and UV observations reveal ongoing processes hidden beneath the glow of older stars. Future missions, particularly in far infrared and submillimeter wavelengths, will allow even more detailed mapping of M64's cold dust and molecular gas. Observations with JWST and ALMA already push the limits, but improved sensitivity will reveal smaller star-forming clumps, finer turbulent structures, and the faintest streams of gas feeding the central regions. Scientists anticipate that these observations will clarify how the counter-rotating disks interact at a microphysical level, how shocks, shear, and turbulence regulate star formation and chemical mixing in unprecedented detail. What the Black-Eye Galaxy tells us about cosmic evolution. One of the most important lessons from M64 is the role of galactic mergers in cosmic evolution. The counter-rotating disks of gas are clear evidence that a smaller, gas-rich galaxy collided with M64 approximately 1 billion years ago. This was not a catastrophic collision like those that form massive elliptical galaxies, but a minor merger, a subtle yet transformative event. It altered the galaxy's dynamics without destroying its spiral structure, leaving behind the dark dust ring that continues to fuel new star formation. Minor mergers like this are common in the universe. Large galaxies grow over time by absorbing smaller companions, gradually increasing their mass and complexity. M64 demonstrates how even a single minor merger can leave lasting imprints. The infalling gas settled into an opposite rotation, creating turbulence and shear that trigger bursts of star formation. The merger also left a chemical signature, lower metallicity gas in the outer disk, contrasting with the metal-rich inner stars. By analyzing these features, astronomers can reconstruct the galaxy's interaction history with remarkable precision. Comparing M64 to the Milky Way offers further perspective. In about 4 billion years, the Milky Way will collide with the Andromeda Galaxy. While that event will involve two massive galaxies of similar size, many of the same processes observed in M64 will occur on a larger scale. Gas will be redistributed, new stars will form, and turbulence will affect the structure of the merged system. Observing M64 today provides a preview of the physical and chemical processes that will take place in our own galaxy's future. M64 also provides a unique opportunity to study counter-rotating systems. Such galaxies are rare, and their unusual motion allows astronomers to explore how angular momentum is transferred during mergers. In the case of M64, the outer gas disk rotates opposite to the inner stars, a direct result of the infalling galaxy's orientation and velocity at the time of collision. This counter-rotation creates zones of shear, where opposing flows meet and compress the interstellar medium. These zones become sites of intense star formation, showing how angular momentum affects the rate and distribution of stellar birth. Studying counter-rotating systems helps refine models of galactic dynamics. Simulations based on M64 show how energy and momentum are redistributed during mergers. They explain how a galaxy can maintain a stable spiral structure even when its gas disks move in opposing directions. This challenges older assumptions that minor mergers must lead to chaotic systems or the complete disruption of disk galaxies. M64 demonstrates that galaxies can absorb smaller companions, create complex internal motions, and still emerge as organized spiral structures. The galaxy also teaches astronomers about star formation under extreme conditions. The shear forces at the interface of the two disks compress gas in ways different from standard spiral density waves. Molecular clouds in the dark ring collapse more efficiently, forming clusters of massive young stars. Observing these regions provides a natural laboratory for understanding how environmental factors influence stellar evolution, including the formation of massive stars and the timing of supernova explosions. These insights are not limited to M64. They can be applied to other systems with unusual gas dynamics, helping astronomers generalize the processes that govern star formation across the universe. Beyond dynamics and star formation, M64 exemplifies resilience in galactic evolution. Despite the violent merger in its past, the galaxy has settled into a graceful, symmetric spiral. Its central bulge remains dense and metal-rich, while the dark ring continues to nurture new stars. This resilience is an important lesson for understanding galaxy morphology. Even after significant interactions, disk galaxies can survive and continue evolving for billions of years. M64 shows that a galaxy's form is not permanently destroyed by minor mergers. Instead, it adapts, reorganizes, and continues its cycle of star formation and chemical enrichment. Observations of M64 also shed light on the interplay between gas, dust, and stellar populations. The chemical fingerprint of the galaxy, differences in metallicity between the inner and outer regions, reveals how mergers redistribute matter. Older stars in the core carry the signature of the galaxy's long history, while younger stars in the dark ring bear evidence of recent infall and compression. This contrast provides a timeline, allowing astronomers to measure the relative ages of stellar populations and the impact of mergers on star formation. M64 informs our understanding of galactic ecosystems. The counter-rotating disks, turbulent dust lane, and chemical gradients illustrate how galaxies recycle and redistribute matter. Gas inflows, star formation, supernova feedback, and magnetic field interactions work together to maintain equilibrium over billions of years. By observing this balance in M64, scientists can test theoretical models of galaxy evolution and improve predictions for other systems, including our own Milky Way. Even the seemingly quiet supermassive black hole at M64's center provides insights. Although it is not actively accreting large amounts of gas, its presence affects the motion of stars in the core. Measuring stellar velocity dispersion allows astronomers to estimate the black hole's mass, providing another piece of the puzzle in understanding how central black holes and galactic disks co-evolve after mergers. Observing M64 today gives astronomers a snapshot of a galaxy shaped by the past, but it also raises questions about its future. What will become of this counter-rotating spiral as it drifts slowly within the Virgo supercluster? How will the interplay of gas, dust, and star formation continue to shape its evolution over billions of years? The answers lie in understanding both the galaxy's current trajectory and the processes that govern long-term galactic development.